Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. One, you die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014+81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our Sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a googol years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will have become uninhabitable long before then. This is not the end of our story. There are loads more interesting ideas about black holes. We'll explore them in part 2. Matter as we know it. Atoms, stars and galaxies, planets and trees, rocks and us. This matter accounts for less than 5% of the known universe. About 25% is dark matter and 70% dark energy, both of which are invisible. This is kind of strange because it suggests that everything we experience is really only a tiny fraction of reality. But it gets worse. We really have no clue what dark matter and energy are or how they work. We are pretty sure they exist though. So, what do we know? Dark matter is the stuff that makes it possible for galaxies to exist. When we calculated why the universe is structured the way it is, it quickly became clear that there's just not enough normal matter. The gravity of the visible matter is not strong enough to form galaxies and complex structures. Stars would more likely be scattered all over the place and not form galaxies. So we know there is something else inside and around them. Something that doesn't emit or reflect light. Something dark. But besides being able to calculate the existence of dark matter, we can see it, kind of. Places with a high concentration of dark matter bend light passing nearby, so we know there's something there that interacts with gravity. Right now, we have more ideas about what dark energy is not than what it is. We know dark matter is not just clouds of normal matter without stars because it would emit particles we could detect. Dark matter is not antimatter because antimatter produces unique gamma rays when it reacts with normal matter. Dark matter is also not made up of black holes, very compact objects that violently affect their surroundings, while dark matter seems to be scattered all over the place. Basically, we only know 3 things for sure. 1. Something is out there. 2. It interacts with gravity. 3. There is a lot of it. Dark matter is probably made up of a complicated exotic particle that doesn't interact with light and matter in a way we expect, but right now, we just don't know. Dark energy is even more strange and mysterious. We can't detect it, we can't measure it, and we can't taste it, but we do see its effects very clearly. In 1929, Edwin Hubble examined how the wavelength of light emitted by distant galaxies shifts towards the red end of the electromagnetic spectrum as it travels through space. He found that fainter, more distant galaxies showed a large degree of redshift. Closer galaxies, not so much. Hubble determined that this was because the universe itself is expanding. The redshift occurs because the wavelengths of light are stretched as the universe expands. More recent discoveries have shown that the expansion of the universe is accelerating. Before that, it was thought that the pull of gravity would cause the expansion to either slow down or even retract and collapse in on itself at some point. Space doesn't change its properties as it expands. There's just more of it. New space is constantly created everywhere. Galaxies are tight-bound clusters of stuff held together by gravity, so we don't experience this expansion in our daily lives, but we see it everywhere around us. Wherever there is empty space in the universe, more is forming every second. So dark energy seems to be some kind of energy intrinsic to empty space. Energy that is stronger than anything else we know and that keeps getting stronger as time passes by. Empty space has more energy than everything else in the universe combined. We have multiple ideas about what dark energy might be. One idea is that dark energy is not a thing, but just a property of space. Empty space is not nothing, it has its own energy. It can generate more space and is quite active. So as the universe expands, it could be that just more and more space appears to fill the gaps, and this leads to a faster expanding universe. This idea is close to an idea that Einstein had back in 1917 of a concept of a cosmological constant, a force that counteracted the force of gravity. The only problem is that when we tried to calculate the amount of this energy, the result was so wrong and weird that it only added to the confusion. Another idea is that empty space is actually full of temporary, virtual particles that spontaneously and continually form from nothing and then disappear into nothing again. The energy from those particles could be dark energy. Or maybe dark energy is an unknown kind of dynamic energy fluid or field which permeates the entire universe but somehow has the opposite effect on the universe than normal energy and matter. But if it exists, we don't know how and where, or how we could detect it. So there are still a lot of questions to answer. Our theories about dark matter and dark energy are still just that, theories. On the one hand, this is kind of frustrating. On the other hand, this is frontier science, making it very exciting. It shows us that no matter how much we feel we're on top of things, we're still very much apes with smartphones, on a tiny, fragile island in space, looking into the sky, wondering how our universe works. There is so much left to learn, and that is awesome. Neutron stars are one of the most extreme and violent things in the universe. Giant atomic nuclei only a few kilometers in diameter but as massive as stars. And they owe their existence to the death of something majestic. Stars exist because of a fragile balance. The mass of millions of billions of trillions of tons of hot plasma are being pulled inwards by gravity and squeeze material together with so much force that nuclei fuse. Hydrogen fuses into helium. This releases energy which pushes against gravity and tries to escape. As long as this balance exists, stars are pretty stable. Eventually, the hydrogen will be exhausted. Medium stars like our Sun go through a giant phase where they burn helium into carbon and oxygen before they eventually turn into white dwarfs. But in stars many times the mass of our Sun, things get interesting when the helium is exhausted. For a moment, the balance of pressure and radiation tips and gravity wins, squeezing the star tighter than before. The core burns hotter and faster while the outer layers of the star swell by hundreds of times, fusing heavier and heavier elements. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a day. And then, death. Iron is nuclear ash. It has no energy to give and cannot be fused. The fusion suddenly stops and the balance ends. Without the outward pressure from fusion, the core is crushed by the enormous weight of the star above it. What happens now is awesome and scary. Particles like electrons and protons really don't want to be near each other. But the pressure of the collapsing star is so great that electrons and protons fuse into neutrons, which then get squeezed together as tightly as in atomic nuclei. An iron ball the size of the Earth is squeezed into a ball of pure nuclear matter the size of a city. But not just the core, the whole star implodes, gravity pulling the outer layers in at 25% the speed of light. This implosion bounces off the iron core, producing a shock wave that explodes outwards and catapults the rest of the star into space. This is what we call a supernova explosion, and it will outshine entire galaxies. What remains of the star is now a neutron star. Its mass is around 1 million times the mass of the Earth, but compressed to an object about 25 kilometers wide. It's so dense that the mass of all living humans would fit into 1 cubic centimeter of neutron star matter. That's roughly 1 billion tons in a space the size of a sugar cube. Put another way, that's Mount Everest in a cup of coffee. From the outside, a neutron star is unbelievably extreme. Its gravity is the strongest outside black holes, and if it were any denser, it would become one. Light is bent around it, meaning you can see the front and parts of the back. Their surfaces reach 1 million degrees Celsius compared to a measly 6,000 degrees for our Sun. Okay, let's look inside a neutron star. Although these giant atomic nuclei are stars, in many ways they're also like planets with solid crusts over a liquid core. The crust is extremely hard. The outermost layers are made of iron left over from the supernova, squeezed together in a crystal lattice with a sea of electrons flowing through them. Going deeper, gravity squeezes nuclei closer together. We find fewer and fewer protons as most merge to neutrons, until we reach the base of the crust. Here, nuclei are squeezed together so hard that they start to touch. Protons and neutrons rearrange, making long cylinders or sheets, enormous nuclei with millions of protons and neutrons shaped like spaghetti and lasagna, which physicists call nuclear pasta. Nuclear pasta is so dense that it may be the strongest material in the universe, basically unbreakable. Lumps of pasta inside a neutron star can even make mountains, at most a few centimeters high, but many times as massive as the Himalayas. Eventually, beneath the pasta, we reach the core. We're not really sure what the properties of matter are when they're squeezed this hard. Protons and neutrons might dissolve into an ocean of quarks, a so-called quark-gluon plasma. Some of those quarks might turn into strange quarks, making a sort of strange matter with properties so extreme that we made a whole video about it. Or maybe they just stay protons and neutrons. No one knows for sure, and that's why we do science. That's all pretty heavy stuff, literally, so let's go back out into space. When neutron stars first collapse, they begin to spin very, very fast, like a ballerina pulling her arms in. Neutron stars are celestial ballerinas spinning many times per second. This creates pulses because their magnetic field creates a beam of radio waves which passes every time they spin. These radio pulsars are the best known type of neutron star. About 2,000 are known of in the Milky Way. These magnetic fields are the strongest in the universe, a quadrillion times stronger than Earth's after they're born. They're called magnetars until they calm down a little. But the absolute best kind of neutron stars are friends with other neutron stars. By radiating away energy as gravitational waves, ripples in space-time, their orbits can decay and they can crash into and kill each other in a kilonova explosion that spews out a lot of their guts. When they do, the conditions become so extreme that for a moment, heavy nuclei are made again. It's not fusion putting nuclei together this time, but heavy neutron-rich matter falling apart and reassembling. Only very recently, we've learned that this is probably the origin of most of the heavy elements in the universe, like gold, uranium and platinum, and dozens more. So there now, two neutron stars collapse and become a black hole, dying yet again. Not only do stars have to die to create elements, they have to die twice. Over millions of years, these atoms will mix back into the galaxy, but some of them end up in a cloud which gravity pulls together to form stars and planets, repeating the cycle. Our solar system is one example, and the remains of those neutron stars that came before us are all around us. Our entire technological modern world was built out of the elements neutron stars made in eons past, sending these atoms on a 13 billion year journey to come together and make us and our world. And that's pretty cool. The universe looks like a vast empty ocean sprinkled with rare islands of galaxies. But this is an illusion. Just a small fraction of all atoms are found in galaxies, while the rest is thought to be drifting in between, in the intergalactic medium. Like the roots of some massive tree, gas spreads out from each galaxy, gravity funneling fresh mass into this dense cosmic forest. Here in the intergalactic medium are the raw materials of creation: hydrogen and helium, woven into sheets and filaments that flow into galaxies where they eventually create stars. But if we look closely, we see who's actually in charge: quasars, the single most powerful objects in existence. As small as a grain of sand compared to the Amazon River, they reside in the centers of some galaxies, shining with the power of 1 trillion stars, blasting out huge jets of matter, completely reshaping the cosmos around them. They're so powerful that they can kill a galaxy. What are they, and how do they mold the structure of the universe at their whim? Everywhere you look, Weird things in the sky. In the 1950s, astronomers noticed mysterious loud radio waves coming from spots all over the sky. They were named quasi-stellar radio sources, or quasars, because they were dots like stars but were seen in radio waves rather than visible light. Everything about them was strange. Some flickered, others emitted high-energy X-rays in addition to radio waves, but all seemed to be tiny. They all moved extremely fast, as much as over 30% the speed of light. The only explanation was that they must have been so distant that their apparent speed was actually the expansion of the universe moving them away from us. But these enormous distances meant that quasars couldn't just be stars, but the active cores of galaxies billions of light years away. And it gets crazier. To appear so bright and loud, given these vast distances, they are thousands of times brighter than the entire Milky Way. Monsters exploding and screaming into the void with a violence not thought possible before. As we mapped the sky, we discovered over 1 million quasars, and they all seem to be very far away. Looking into space far away means very long ago, because light takes so long to reach us. Quasars were common in the early universe, having peaked in number 10 billion years ago when galaxies and the universe itself were still very young. Let's go back in time just 3 billion years after the Big Bang and see what was going on back then. The incredible power of quasars. How could an early baby galaxy be so incredibly bright and violent? All that light and radiation couldn't be stars, as there weren't nearly enough of them. And since galaxies tend to grow with time by merging, the starlight from small galaxies shouldn't be far brighter than any galaxy today. There's only one way to generate the vast amounts of energy a quasar shines with: feeding supermassive black holes. We still don't know how exactly they formed, but it seems that every galaxy has one in their center. But how can the brightest things in the universe be black holes which trap anything and everything that crosses their event horizon? Well, the light of a quasar is not coming from inside these black holes. Rather, it comes from the space around them, a massive orbiting disk of gas called an accretion disk. Quasars use the same fuel as stars to shine: matter. It's just that black holes are the most efficient engines for converting matter into energy in the universe. The energy released by matter falling into a black hole can be 60 times greater than that released by nuclear fusion in the core of a star, because the energy released by a black hole comes from gravity, not from nuclear reactions. Matter falling into a black hole speeds up to almost the speed of light before it crosses the event horizon, buzzing with an incredible amount of kinetic energy. Of course, once inside the black hole, it takes that energy with it. You only get to witness this energy if you drop your matter in the right way, fall straight down, and the outside universe gets nothing. But when you have a lot of matter, it spirals in incredibly fast towards the event horizon, forming a disk. Collisions between particles and friction heat it up to hundreds of thousands of degrees. In a space not much bigger than our solar system, the core of a galaxy can release many times more energy than all its stars combined. This is what a quasar is: a supermassive black hole having a feast. And these black holes eat a lot. Typical quasars consume 1 to 100 Earth masses of gas per minute. 10 billion years ago, the universe was about a third of its current size, so the intergalactic medium was much less spread out, meaning the filaments of gas around quasars could feed them a banquet, making them vomit insane amounts of light and radiation. The brightest quasars power jets, tangling the magnetic field of the matter around them into a narrow cone. Like a particle accelerator, they launch enormous beams of matter out, plowing through the circumgalactic medium, forming plumes of matter that grow to hundreds of thousands of light years in size. It's almost unfathomable in scale. A tiny spot in a galaxy carving out patches of the universe hundreds of thousands of light years long. But quasars can't eat for long, maybe a few million years, because their feast ultimately kills their galaxy. How quasars kill galaxies. Okay, maybe killing is a bit of an exaggeration. A galaxy is still there after its quasar turns off, but it will never be the same again. Quasars, being among the hottest and brightest things in the universe, break their galaxies by heating them up too much and stopping star formation. Stars are gas that collapsed in on itself and then got really hot. But in a cloud of gas that's already hot, atoms are moving quickly. When they collide, they hit hard, exerting pressure that resists gravity's squeeze. So hot gas cannot form stars. Instead, the best gas for forming stars is already cold and won't put up a fight when it's time to collapse into a star. On top of that, quasars push gas out of their galaxies. Not only does this starve the quasar, but its galaxy loses the raw materials for new stars. As sad as this sounds, it might be a good thing for life. The alternative can be far more dangerous: too many stars. New stars forming is usually followed by massive stars exploding in supernovae, so planets would be burned sterile. But of course, it's more complicated. Like the intricacies of our own planet's biosphere, every piece of the galaxy is dependent on and influencing every other part of the galactic environment. While hot things like quasars and supernovae tend to push gas out of the galaxy, shockwaves and quasar jets can also compress gas, making new stars at least for a short time. But in general, we can say that without things becoming a bit more chill, we would not exist today. Which brings us to our final question. Did the Milky Way have a quasar in the past? It's unclear if every galaxy went through a quasar phase, but understanding distant quasars may provide clues to the history of the Milky Way. Galaxies don't do a good job of preserving their history. Like sand on a beach, the endless churning mixes away the clues to their past. It's possible the Milky Way was once a quasar, which may have allowed our supermassive black hole Sagittarius A star to have grown to 4 million times the mass of the Sun. And as dormant as it is now, Sagittarius A star could turn into a quasar in the future. In a few billion years, the Milky Way will merge with Andromeda. We've seen over 100 double quasars in galaxies smashing together, where fresh gas is provided for the central black holes. But it won't last for long. When galaxies merge, so do their supermassive black holes, sinking into the center of their new galaxy, kicking up dust and stars in every direction. We don't know whether this will happen, but it would truly be an incredible sight. Maybe some beings in the far future are going to witness it and be in awe of what they see. One day the last star will die and the universe will turn dark forever. It will probably be a red dwarf, a tiny kind of star that's also one of our best bets to find alien life and might be the last home of humanity before the universe becomes uninhabitable. So what do we know about them, and why are they our last hope? At least 70% of stars in the universe are red dwarfs. They are the tiniest stars out there, with only about 7 to 50% of the mass of our Sun, not that much bigger than our planet Jupiter, which is still huge though. They are also very dim. It's impossible to see them with the naked eye. You've never seen one in the night sky. Even with all our technology, we can only clearly observe red dwarfs in our neighborhood. Approximately 20 of the 30 stars close to Earth are red dwarfs. Like all stars, red dwarfs fuse hydrogen into helium. But while more massive stars accumulate all the fused helium in their cores, red dwarfs stay convective, meaning that the helium and hydrogen constantly mix. So they use up their fuel incredibly slowly before they're extinguished. Red dwarfs burn so slowly that their average lifespan is between 1 and 10 trillion years. By comparison, the Sun will survive for another 5 billion years. Because the universe is only 13.75 billion years old, not a single red dwarf has reached later development stages. Every single one of the trillions that exist is still a baby. Speaking of babies, the smallest star in the entire universe is also a red dwarf, because small red dwarfs are right on the verge of being a star at all. Just a tiny bit less hydrogen, and they are mere brown dwarfs, failed stars that cannot sustain a fusion reaction for long. So what about aliens, or a new home for humanity? Since our Sun will die one day, we'll eventually need to look for a new home. And where there are habitable planets, there might also be aliens. The Kepler Space Observatory found that at least half of all red dwarfs host rock planets between 1/2 and 4 times the mass of our Earth. Many of them are in the habitable zone, the area around a star where water can be liquid. But since red dwarfs burn at relatively cold temperatures, a planet would need to be really close to be hospitable, probably as close as Mercury to our Sun, or even closer. Which brings with it all kinds of problems. For example, a planet this close to a star would probably be tidally locked, meaning the same side would always face it. This side would be incredibly hot, while the shadow side would be frozen, which makes it hard for life to develop. Although a planet with a big enough ocean might be able to distribute the star's energy and create some kind of stability. Or the gravitational forces of the red dwarf could squeeze the planet and heat it up so much that it might lose all its water over time. These planets could end up like Venus, a hot, burning hell. Another problem is that many red dwarfs vary in their energy output. They can be covered in star spots that can dim their emitted light by up to 40% for months, which would cause oceans on planets to freeze over. At other times, they can emit powerful solar flares, sudden outbursts of energy, incredibly powerful. These red dwarfs can double their brightness in minutes, which could strip away sizable portions of a planet's atmosphere and burn it, rendering it sterile. On the other hand, their extremely long lifespan is a big plus. A red dwarf with just moderate levels of activity could be an amazing place for a planet that hosts life. Life on Earth has existed for about 4 billion years, and we have about 1 billion years left before the Sun becomes so hot that complex life on Earth will become impossible. We will either die out or leave Earth and look for a new home. We could build a civilization for potentially trillions of years around a red dwarf with the right conditions. About 5% of the red dwarfs in the Milky Way may host habitable, roughly Earth-sized planets. That would be more than 4 billion in total. But life may not even need a planet like Earth. Candidates for life around a red dwarf may be the moons of gas giants, or so-called super-Earths, really massive rocky planets. All in all, there are an estimated 60 billion potentially habitable planets around red dwarfs, and that's in the Milky Way alone. So red dwarfs might become really important for our survival in the future. But everything has to die at some point, even red dwarfs. When in trillions of years the life of the last red dwarf in the universe is about to end, it will not be a very spectacular event. As its hydrogen runs out, it shrinks, becoming a blue dwarf, burning out completely. After its fuel is spent, it's transformed into a white dwarf, an object about as small as Earth, packed very densely and made of degenerate gases, mostly of helium-4 nuclei. Having no more source of energy, it will cool extremely slowly over trillions of years until it becomes its final form, a cold black dwarf. White and black dwarfs are so fascinating that they deserve their own video. Anyway, it's going to be a long time before the last stars in the universe vanish. It's kind of uplifting to know that if humanity succeeds in venturing into space, we have plenty of time before the universe turns out the lights. What is the true nature of the universe? To answer this question, humans come up with stories to describe the world. We test our stories and learn what to keep and what to throw away. But the more we learn, the more complicated and weird our stories become. Some of them so much so that it's really hard to know what they're actually about. Like string theory, a famous, controversial and often misunderstood story about the nature of everything. Why did we come up with it, and is it correct, or just an idea we should chuck? To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots, all of them made from structures of molecules made up of countless, even smaller things, atoms. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided anymore, elementary particles. But now we had a problem. They're so small that we could no longer look at them. Think about it. What is seeing? To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye. The wave carries information from the object that your brain uses to create an image. So you can't see something without somehow interacting with it. Seeing is touching, an active process, not a passive one. This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But in quantum physics, shorter wavelengths means more energy. So when we touch a particle with a wave that has a lot of energy, it gets a kick. By looking at a particle, we change it. In quantum physics, we cannot know where a particle is and where it's going with absolute precision. This fact is so important that it has a name: the Heisenberg uncertainty principle, the basis of all quantum physics. So what does a particle look like then? What is its nature? We don't know. If we look really hard, we can see a blurry sphere of influence, but not the particles themselves. We just know they exist. But if that's the case, how can we do any science with them? We did what humans do and invented a new story, a mathematical fiction. The story of the point particle. We decided that we would pretend that a particle is a point in space. Any electron is a point with a certain electric charge and a certain mass, all indistinguishable from each other. This way, physicists could define them and calculate all of their interactions. This can be made precise in quantum field theory, and this solved a lot of problems. All of the standard model of particle physics is built on it, and it predicts lots of things very well. Some quantum properties of the electron, for example, have been tested and are accurate up to 0.0000000000002%. So while particles are not really points, by treating them as if they were, we get a pretty good picture of the universe. Not only did this idea advance science, it also led to a lot of real-world technology we use every day. But there's a huge problem: gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage. To put it simply, gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down. And this is a big problem. If we could marry gravity to quantum physics and the standard model, we would have the theory of everything. So very smart people came up with a new story. They asked, what is more complex than a point? A line or a string? String theory was born. What makes string theory so elegant is that it describes many different elementary particles as different modes of vibration of the string. Just like a violin string vibrating differently can give you a lot of different notes, a string can give you different particles. Most importantly, this includes gravity. String theory promised to unify all fundamental forces of the universe. This caused enormous excitement and hype. String theory quickly graduated to a possible theory of everything. Unfortunately, string theory comes with a lot of strings attached. Much of the maths involving a consistent string theory does not work in our universe with its 3 spatial and 1 temporal dimensions. String theory requires 10 dimensions to work out. So string theorists did calculations in model universes, and then try to get rid of the 6 additional dimensions and describe our own universe. But so far, nobody has succeeded, and no prediction of string theory has been proven in an experiment. So string theory did not reveal the nature of our universe. One could argue that in this case, string theory really isn't useful at all. Science is all about experiments and predictions. If we can't do those, why should we bother with strings? It really is all about how we use it. Physics is based on maths. 2 + 2 makes 4. This is true no matter how you feel about it. And the maths in string theory does work out. That's why string theory is still useful. Imagine that you want to build a cruise ship, but you only have blueprints for a small rowing boat. There are plenty of differences: the engine, the materials, the scale. But both things are fundamentally the same: things that float. So by studying the rowing boat blueprints, you might still learn something about how to build a cruise ship eventually. With string theory, we can try to answer some questions about quantum gravity that have been puzzling physicists for decades, such as how black holes work or the information paradox. String theory may point us in the right direction. When used in this spirit, string theory becomes a precious tool for theoretical physicists and help them discover new aspects of the quantum world and some beautiful mathematics. So maybe the story of string theory is not the theory of everything. But just like the story of the point particle, it may be an extremely useful story. We don't yet know what the true nature of reality is, but we'll keep coming up with stories to try and find out until one day, hopefully, we do know. What if our universe comes with a self-destruct button to eliminate itself so cleanly and efficiently that every single physical thing would just stop existing and life would be impossible forever? The ultimate ecological catastrophe: vacuum decay. To explain how our universe could destroy itself, we need to understand two principles. 1. Energy levels. A core idea in physics is that everything has an energy level. The higher the level, the more energy is in the system. Wood, for example, has a high level. It can be burned, a process that releases the chemical energy stored in its molecular bonds and turns it into heat. The ash left over is at a lower energy level than the wood before. 2. Stability. Everything in our universe tries to move towards its ground state, in which it's completely stable and has as little energy as possible. For example, a ball on a hill is unstable and has a lot of potential energy. When disturbed, it will roll down into the valley and lose its potential energy in the process. The ball is now in its ground state and stable. It will remain like that. Everything in our universe follows these two principles. If something has a lot of energy, it's unstable and wants to get rid of it to become stable and reach its ground state. This is true for every system, even in the weird world of quantum mechanics. If our current understanding of physics is correct, then the universe gets its properties from quantum fields. We explained them in detail in another video. For this video, imagine them as the rules of the universe. They tell particles how to behave and interact. Like everything in the universe, they want to be in the lowest energy level possible, which is called a vacuum state. This has nothing to do with vacuum in space. It's just called this way because scientists are bad at naming things. We think all the fields reached their vacuum state, except maybe one. It's possible that the Higgs field is not stable but metastable, which is a fancy way of saying that it pretends to be stable but really is not. It would be a false vacuum. The Higgs field is responsible for giving particles their mass, which rules how almost everything in the universe interacts. What would happen if the Higgs field is in a false vacuum? Think of our ball in the valley. The ball is the Higgs field. The valley might not be the lowest energy state for the Higgs field. There might be an even deeper valley that it wants to get to. This would mean that the Higgs field has a lot of potential energy waiting to be released. The Higgs field could be like a piece of wood, but drenched in gasoline, waiting to set the universe on fire. A random spark, like quantum tunneling, could release the potential energy of the Higgs field. This could happen at any time and without warning. If at any point in space this so-called vacuum decay starts, there is no turning back. As the Higgs field crashes into the lower energy state, it releases a massive amount of potential energy. This energy pushes the space around it over the barrier, which releases more potential energy. A sphere of the new stable Higgs field or true vacuum grows at the speed of light in all directions. Imagine it like setting a sea of gasoline the size of the universe on fire. The sphere is surrounded by a shell of energy that devours everything it comes into contact with. Whatever it touches is eliminated from existence. The bubble will continue to grow forever, deleting the universe on its way. There is no way to be warned since it's so fast, but there's nothing we could do anyway. Our destruction would be instant. In a fraction of a second, Earth would be gone. But it actually gets worse. If the energy level of the Higgs field changes, it changes all of physics. In the true vacuum of the sphere, the standard model will be overthrown, superseded by different physics that we don't know. How fundamental particles behave, how atoms hold together, how chemicals react. Vacuum decay won't just destroy life, it will destroy chemistry itself, making life as we know it impossible. We simply have no idea what it would be like inside. It might be a shadow of what it is now. Or not. We don't know. If vacuum decay happens, the outlook is indeed grim. If you feel slightly worried now, don't be. At this point, false vacuum is speculation based on our current understanding of particle physics, which might be wrong. It's kind of like using a ruler to measure a continent. Sure, you can do it, but you might be off by quite a bit at the end. Right now, no one can say if vacuum decay is a thing that's real or just a scary idea. But even if one or multiple spheres of death have already started expanding, the universe is so big that they might not reach us for billions of years. If they're far enough away, they might not ever be able to reach us because of the expansion of the universe. The speed of light is not that fast on the scale of the universe. So while vacuum decay is fascinatingly scary, right now there are other things we should be more afraid of. In contrast to vacuum decay, we have the power to prepare for most of them. Black holes are the largest collections of pure, violent energy in the universe. If you come too close, they'll devour you and add your energy to their collection. And so, the energy is lost to us forever. Or is it? It turns out there's a universe cheat code. A way of powering civilizations until the very death of everything, or of constructing the largest bomb in the universe. But how? Didn't we learn that all energy is trapped forever in black holes, even light? This is true. Everything you think you know about the weirdest thing in the universe is about to get weirder for one simple reason. Black holes are spinning. Why black holes spin? When really massive stars die, their cores collapse under their own gravity into black holes. This means something very big becomes very tiny. Like the tiniest anything can be in this universe. But stars are rotating, and a fundamental property of our universe is that things that are spinning don't want to stop spinning. We call this angular momentum. And this angular momentum can't go away. A big thing that spins and becomes smaller spins faster. So, as the core of a star collapses, its momentum makes it spin faster and faster and faster until it collapses into a black hole. And the black hole keeps on spinning, inconceivably fast. Some of them spin millions of times a second. Why spinning black holes are special? Just like non-spinning black holes, spinning black holes have an event horizon and a singularity at their core where all of their mass is concentrated. The singularity is usually described as a single, infinitely small point with no surface area. But points can't rotate, so a rotating singularity can't be a point. Instead, it's a ringularity. A ringularity is a ring with a thickness of 0 and no surface, spinning extremely fast, containing all the mass of the black hole. The black hole is spinning so fast that it morphs space and time itself. It literally drags space with it, such is its power. This creates a new and super weird region of space-time, the ergosphere, which envelops the black hole. If space and time are completely broken inside the event horizon, then they're only half broken inside the ergosphere. Inside the ergosphere, nothing makes sense. It's possible to enter it and then leave it again, but it's probably not a great experience. You can imagine it like this. Falling into a static black hole is like sliding down a hole. Being inside the ergosphere of a spinning black hole is like spiraling down a deadly drain. The black hole transfers its own kinetic energy in the form of rotation to everything that enters the ergosphere. The ringularity makes you dance whether you want to or not. You need to move faster than the speed of light just to stand still here, which is impossible. But here's our cheat code. We can steal this energy. And there's a lot of energy to steal. How to steal energy from a monster. Take the supermassive black hole at the center of the Milky Way. We could steal as much energy from it as every single star in the Milky Way emits in 1 billion years combined. The easiest way to steal this energy is, oddly enough, to drop something into the black hole. We've seen that the Ringularity forces energy on us when we enter the ergosphere, which is a lot like being in a whirlpool with space-time rushing around and around. If you're clever, you can use the water to your advantage and swim faster than before. In practice, this means sending a rocket into the ergosphere and making a trade with the black hole. We give it some mass energy, and it gives us some of its rotational energy. But it's not a fair trade, we get the better deal. Normally, if you fire a rocket, you exchange chemical energy for kinetic energy. This is like pushing yourself forward in a swimming pool. But if you fire a rocket inside the ergosphere, it's like pushing yourself forward in a wave pool. The rotational energy of the waves gives you a much stronger boost than you could get just by pushing yourself. The boost from the rotation of the black hole is so big that you leave the ergosphere with much more energy than you entered it. The black hole gives a tiny amount of its rotational energy to you and slows down a little. Obviously, this requires a lot of food. Fortunately, black holes aren't picky eaters. An advanced future civilization would probably harvest asteroids to drop them into the black hole when they needed an energy boost. But there's an even better way to get energy from a black hole, and oddly enough, it builds the biggest bomb any living thing could ever hope to build. The black hole bomb. We only need two things to build a black hole bomb: a fast-spinning black hole and a big mirror. The mirror has to completely envelop the black hole, which is similar to a Dyson sphere, a megastructure that harvests the energy of an entire star. Although our mirror would be easier to build, mirrors are simpler and black holes are much more compact than stars. If we made the mirror 10 centimeters thick, the metal of a big asteroid would probably be enough material for a black hole with the mass of our Sun. Once our mirror is in place, we only need to open a window and shoot electromagnetic waves at the black hole. You can imagine what happens next by imagining tossing a ball at a wall and it coming back faster than a bullet. The waves hit the black hole at light speed. A small proportion of the waves falls past the event horizon to disappear forever. But a much larger amount sloshes through the ergosphere, where the black hole forces some of its rotational energy on them and amplifies them. They now begin super radiant scattering, which are fancy science words meaning bouncing around between mirror and black hole and getting stronger. Every time they go around, they are getting exponentially stronger. By opening some windows in the mirror, we can extract the energy from the waves as fast as they grow, which we could use, in theory, to create what would be, for all practical purposes, an endless source of energy for trillions of years. Or we could blow it up. If the waves are not released, they will continue to get stronger and stronger and take more and more energy from the black hole until the mirror shatters. A supermassive black hole would release as much energy as a supernova, making the bomb the largest explosion any living being could ever create. The last home in a dying universe. The beauty of the black hole bomb, the Penrose process, and the super radiant scattering is that they are not science fiction. In the far, far future, this might be the only way to survive in our dying universe. After all the red dwarfs have cooled down and all the white dwarfs transformed into black dwarfs, the universe will turn dark forever. Rotating black holes might be the only sources of energy in the entire universe that life could harvest. If so, the last living being in existence might one day end its life around a black hole, which is equally chilling and uplifting. It turns out that even without any light, there are places we can go. Neutron stars are the densest things that are not black holes. In their cores, we might find the most dangerous substance in existence: strange matter. A bizarre thing so extreme that it bends the rules of the universe and could infect and destroy everything it comes into contact with. Or it could teach us about how the universe began. Maybe both. To understand how extreme strange matter really is, we first need to get a few basics. What is a neutron star, and how does strange matter break the rules of the universe? To get all of this into one video, we'll grossly oversimplify a few things, but we'll provide you with further reading if you want more details. A neutron star is what remains after a very massive star explodes in a supernova. When this happens, the star's core collapses under its own gravity with such a strong inward force that it squeezes nuclei and particles together violently. Electrons are pushed into protons, so they merge and turn into neutrons. All the nothing inside of atoms is suddenly completely filled with particles that really don't want to be close to each other but have no choice. They desperately push back against gravity, against the collapse. If gravity wins, they will become a black hole. If they win, they become a neutron star. This makes neutron stars like giant atomic nuclei the size of a city, but holding the mass of our Sun. And here, things get weird. The environment in the core of neutron stars is so extreme that the rules of nuclear physics change. And this could lead to a strange and extremely dangerous substance. But let's not get ahead of ourselves. We first need to know the rules before we learn how they can be broken. Protons and neutrons, the particles making up the nuclei of atoms, are made up of smaller particles called quarks. Quarks really don't want to be alone. They are what we call confined. You can try to separate them, but the harder you pull, the harder they try to pull themselves back together. If you use a lot of energy, they just use this energy to create new quarks. Quarks only exist together as the building blocks of other particles and have never been observed by themselves. They come in many types, but only two appear to make stable matter: the up and down quarks found in protons and neutrons. All other quarks seem to decay away quickly. But this may be different inside neutron stars. The forces operating in their cores are so extreme that they are actually similar to the universe shortly after the Big Bang. Neutron star cores are like fossils, which can let us peer back in time to the beginning of everything. So learning how quarks behave inside a neutron star is a way of understanding the very nature of the universe itself. One hypothesis is that inside a neutron star core, protons and neutrons deconfine. All the particles crammed shoulder to shoulder dissolve and melt into a sort of bath of quarks. Uncountable numbers of particles become one giant thing made purely from quarks: quark matter. A star made from this is called a quark star, though from the outside it may not look any different than a regular neutron star. Now we can finally talk about the most dangerous substance. If the pressure inside a quark star is great enough, it may get stranger. Literally. In the cores of neutron stars, some of the quarks may be converted into strange quarks. Strange quarks have bizarre nuclear properties, and they are heavier and, for the lack of a better word, stronger. If they turn up, they could create strange matter. Strange matter might be the ideal state of matter: perfectly dense, perfectly stable, indestructible. More stable than any other matter in the universe. So stable that it can exist outside neutron stars. If this is the case, we have a problem. It might be infectious. Every piece of matter it touches might be so impressed by its stability that it would immediately turn it into strange matter too. Protons and neutrons would dissolve and become part of the quark bath, which frees energy and creates more strange matter. The only way to get rid of it would be to throw it into a black hole. But then again, who cares? All of it is inside neutron stars. Except when neutron stars collide with other neutron stars, or black holes, they spew out tremendous amounts of their insides, some of which could include little droplets of strange matter called strangelets. Strangelets are as dense as the core of a neutron star. They could be really small, maybe even subatomic, but even the largest strangelets wouldn't be any bigger than a rocket. These strangelets would drift through the galaxy for millions or billions of years until they meet a star or planet by chance. If one were to strike Earth, it would immediately start converting it into strange matter. The more it converts, the more it would grow. Ultimately, all of the atoms making up Earth would be converted. Earth would become a hot clump of strange matter the size of an asteroid. If a strangelet strikes the Sun, it would collapse into a strange star, eating through it like fire through a dry forest. This would not change the Sun's mass much, but it would become way less bright, so Earth would freeze to death. And like a tiny virus, we'd have no way to see a strangelet coming. Worse still, some theories suggest strangelets are more than common, outnumbering all stars in the galaxy. These strangelets could have formed very early after the Big Bang, when it was as hot and dense as a neutron star core everywhere. They might be clumping around the gravity of galaxies as the universe expanded and evolved. Strangelets could even be so numerous and massive that they might actually be the dark matter we suspect holds galaxies together. But then again, maybe not. This is speculation, and the Earth and Sun and planets haven't been consumed in a wildfire of strangelets in the past few billion years, so the odds seem good that it won't happen anytime soon. Understanding these strange objects today may be the key to understanding the birth of our universe and why it grew to look the way it does now. When scientists first started playing with magnets and wires and thinking about electrons, they had no idea how technology would evolve in the next 100 years. The scientists thinking about the cause of neutron stars and strange matter today may be setting up humans for a future beyond our wildest imaginations. Or maybe not. Time will tell. The vast majority of the cosmos is voids. Gigantic, unfathomably large spaces of empty nothingness. Bubbles of eternal night stretching hundreds of millions of light years, almost entirely devoid of galaxies, stars, or light. The loneliest places in existence. Voids are not just the absence of stuff, but weird worlds of darkness that are growing, drifting, colliding, and merging with each other. Inside them, space itself is stretched violently, and it's almost impossible to enter them. Simply put, voids are weird and scary, but they sculpt the entire universe and may ultimately decide its fate. Today, we know of over 8,000 voids and supervoids, and we keep discovering more. No matter how large a cluster or supercluster of galaxies gets, there always seems to be an even larger void nearby. Let's jump off the cosmic cliff and drop into the heart of cosmic nothingness. The loneliest place in the universe. You're zooming away from Earth at thousands of times the speed of light, leaving our solar system and our solar neighborhood behind. Now we see the entire Milky Way with its 200 billion stars and dozens of dwarf galaxies zipping around it. 2.5 million light-years away on a collision course is giant Andromeda and its own swarm of satellite galaxies. We're now moving 1 million times faster than the speed of light, seeing the local group of over 50 galaxies woven together by gravity, rivers of gas, and invisible scaffolds of dark matter. This is our pocket of the universe, 10 million light-years across. No human will ever leave it. Except for you, apparently. As we zoom away even faster, we see the Virgo supercluster, a colossal wall of more than 2,000 galaxies spread over roughly 100 million light-years. Careful now, you're right on the edge of the cosmic cliff where the true deep darkness begins. The local void, a gigantic empty bubble 200 million light-years across. If it was a bright thing and not absolute darkness, it would fill 40% of the night sky we see from Earth. All around us are dozens of such superclusters and gigantic voids filled with suffocating emptiness. You're now traveling towards the greatest and emptiest nothing in existence, right into the center of the Boötes supervoid, a cosmic desert around 300 million light-years wide. So gigantic it should contain thousands of galaxies. But instead, what do you see? You're surrounded by perfect darkness, the most absolute blackness the human mind can conceive. There is no up or down, no motion, nothing to orient yourself. There's not a single sign that the outside universe even exists. It's an inescapable prison, and this isn't some exotic corner of the cosmos. This is how the vast majority of the universe feels to human eyes. Just silent blackness without any movement. Everywhere, forever. Although there is something mysterious hiding in the dark, faint tendrils of dark matter, penetrating into the void like cosmic lichen. a miniature echo of the much larger forest of dark matter filaments that forms the scaffold of galaxies and galaxy clusters outside the void. And at their tips, we find faint bluish specks in the ocean of darkness. Void galaxies, lonely fireflies, unable to light up the night. The rarest galaxies we know, very isolated, very lonely. A universe of bubbles. Before we could look deep into space, astronomers thought we lived in a uniform cosmos with galaxies spread out evenly. But instead, we found that galaxies, cosmic gas, and dark matter were arranged into a vast cosmic web. A recurring pattern of sheets and filaments organized around enormous empty gaps, meeting at dense knots with galaxy clusters and superclusters. But this structure is not static. It just seems to be because the distances between galaxies are so incredibly vast. In reality, galaxies shoot through space at speeds of millions of kilometers per hour. They're on collision courses, orbiting each other, moving towards the center of larger galaxy clusters millions of light years away. But they always seem to stick to the rims of voids like reflections of light on soap bubbles, which is kind of weird. If they're this dynamic, shouldn't a galaxy shoot into a void occasionally? Well, voids are actually extremely hard to enter for galaxies from the outside, at least naturally, because gravity becomes weird at their edges and even weirder deeper inside them. If you didn't know better, you might think voids spit out anything trying to get inside, pushing galaxies to the edge. The way gravity works is that everything with mass in the universe attracts every other thing with mass. And since there's almost no mass inside, the cosmic web of galaxy superclusters on their edges are pulling things out of voids. The emptier a void is, the harder gravity is pulling on what remains. It's really like a tug of war where one side isn't even trying. Over time, voids are really only getting even emptier and the walls and knots around them denser and brighter. Would it be hard to fly into a cosmic void with a spaceship? Well, not technically. The hardest part is escaping the gravity of your home galaxy. It also doesn't make much sense because what exactly do you want to visit inside a void? It makes sense to fly into a void if you want to hide, like really, really hide. But what cosmic horror would be scary enough for a civilization to try to escape into a cosmic void? Galaxies in the crowded cluster regions like our Milky Way are very active. Since its neighbor's gravity tugs and pulls at it, they collide and merge. Void galaxies are so isolated that they're aging in slow motion. They tend to be smaller, bluer, and full of gas, birthing new stars slower and calmer. So void galaxies could be the last places that will stay habitable in our dying universe. The last star in the universe will likely be born here. So maybe in 100 trillion years or so, a desperate alien race will embark on an impossible journey to stretch their existence just a bit longer inside a void galaxy. There's one more thing that makes voids unique places: dark energy, the mysterious force that most scientists think is accelerating the expansion of the universe and will ultimately cause its demise. We can't see dark energy do anything inside our galaxy or inside clusters because there's too much stuff putting things together via gravity, but we can see its effects inside voids. Here, dark energy blows up the bubbles of nothing. This is where the acceleration of cosmic expansion becomes visible. As voids are getting larger and larger, they're breaking the structure of the universe. The beautiful galaxy filaments are slowly being ripped apart. As the emptiness encroaches, walls of thousands of galaxies are thinned out and pulled towards the edges, attracted by much denser regions at the margins, giving space to the emptiness of two void bubbles becoming one. In the far, far future, supervoids will take over the observable universe, crushing clusters and expanding further and further until the entire observable universe is nothing more than a gigantic void of nothingness, the loneliest place in existence. One day the universe will die, but why and how? And will the universe be dead forever? And how do we know that? First of all, the universe is expanding, and not only that, the rate of its expansion is accelerating. The reason? dark energy. Dark energy is a strange phenomenon that scientists believe permeates the universe. Until 1998, we thought that the universe must work a bit like a ball that you throw into the sky. The ball moves up, but at some point it has to come down again. But the expansion of the universe is actually speeding up. That's like throwing a ball up and watching it fly away faster and faster and faster. Where is this acceleration coming from? Well, we don't know, but we call it dark energy. Einstein thought of it first and then decided it was stupid. Now, astrophysicists have decided it is plausible. Trouble is, this is all very theoretical, and we don't actually know what the properties of dark energy are. But there are various theories, and they lead us to 3 scenarios for the end of the universe. 1. The Big Rip. Since its birth, the universe has been expanding. For unknown reasons, new space is created everywhere equally. The space between galaxies expands, so they move apart. The space inside galaxies also expands, but here gravity is strong enough to keep them together. In the Big Rip scenario, the expansion accelerates up to a point where space expands so fast that gravity can't compensate for this effect anymore. The result is a Big Rip. At first, only large structures like galaxies are torn apart since space between the single objects expands very fast. Next, big bodies like black holes, stars, and planets die. Their gravity isn't strong enough to keep them together, so they dissolve into their components. In the end, space would expand faster than the speed of light. Atoms would now be affected, and they would just disband. Once space is expanding faster than light, no particle in the universe can interact with any other particle anymore. The universe would dissolve into countless lonely particles that won't be able to touch anything else in a strange, timeless universe. And you thought you felt lonely. 2. Heat death, or a big freeze. In a nutshell, the difference between the Big Rip and heat death is that in a heat death scenario, matter stays intact and is converted over an incredibly long but finite period of time into radiation while the universe expands forever. But how does this work? Let's talk about entropy. Every system tends towards the state of highest entropy, like when we have a latte macchiato. Initially, it has different regions, but over time they will cool down and disintegrate until it's uniform. And this also applies to the universe. So while the universe gets bigger and bigger, matter slowly decays and spreads out. At some point, after lots of generations of stars, all the gas clouds necessary to form stars will be exhausted, so the universe will turn dark. The remaining suns will die. Black holes will slowly degenerate and evaporate over trillions of years due to what's known as Hawking radiation. When this process is complete, only a dilute gas of photons and light particles remains until even this decays. All activity in the universe ceases at this point. Entropy is at its maximum, and the universe is dead forever. Unless, theoretically, it might be possible that after an incredibly long amount of time, there might be a spontaneous entropy decrease as a result of something called quantum tunneling, leading to a new Big Bang. 3. Big Crunch and Big Bounce. This is the most uplifting scenario. If there is less dark energy than we think, or it decreases over time, gravity will be the dominating force in the universe one day. In a few trillion years, the rate of expansion of the universe will slow down and stop. After that, it reverses. Galaxies will race at each other, merging as the universe becomes smaller and smaller. Since a smaller universe also means a hotter universe, temperatures rise everywhere all at once. 100,000 years before the Big Crunch, background radiation would be hotter than the surfaces of most stars, which means that they would be cooked from the outside. Minutes before the Big Crunch happens, atom cores are ripped apart before supermassive black holes devour everything. Finally, all black holes would merge into a supermassive mega black hole that contains the entire mass of the universe, and in the last moment before the Big Crunch, it would devour the universe, including itself. The Big Bounce theory states that this has happened a lot of times and that the universe goes through an infinite cycle of expansion and contraction. Well, wouldn't that be nice? So what will actually happen to the universe in the end? At the moment, heat death seems the most likely, but we at Kurzgesagt hope that this dead forever stuff is wrong and the universe will start over and over again. We don't know for sure either way, so let's just assume the most uplifting theory is true. What would happen to you if a black hole the size of a coin suddenly appeared near you? Short answer, you'd die. Long answer, it depends. Is it a black hole with the mass of a coin, or is it as wide as a coin? Suppose a US nickel with a mass of about 5 grams magically collapsed into a black hole. This black hole would have a radius of 10 to the power of minus 30 meters. By comparison, a hydrogen atom is about 10 to the power of minus 11 meters. So the black hole compared to an atom is as small as an atom compared to the sun. Unimaginably small. And a small black hole would also have an unimaginably short lifetime to decay by Hawking radiation. It would radiate away what little mass it has in 10 to the power of minus 23 seconds. Its 5 grams of mass will be converted to 450 terajoules of energy, which will lead to an explosion roughly 3 times bigger than the atomic bombs dropped on Hiroshima and Nagasaki combined. In this case, you die. You also lose the coin. If the black hole had the diameter of a common coin, then it would be considerably more massive. In fact, a black hole with the diameter of a nickel would be slightly more massive than the Earth. It would have a surface gravity a billion times greater than our planet currently does. Its tidal forces on you would be so strong that they'd rip your individual cells apart. The black hole would consume you before you even realized what's happening. Although the laws of gravity are still the same, the phenomenon of gravity that you'd experience would be very different around such dense objects. The range of the gravitational attraction extends over the entire observable universe, with gravity getting weaker the farther away you are from something. On Earth right now, your head and your toes are approximately the same distance from the center of our planet. But if you stood on a nickel-sized black hole, your feet would be hundreds of times closer to the center, and the gravitational force would be tens of thousands of times as large as the force on your head and rip you into a billion pieces. But the black hole wouldn't stop with just you. The black hole is now a dominant gravitational piece of the Earth-Moon black hole of death system. You might think that the black hole would sink towards the center of the planet and consume it from the inside out. In fact, the Earth also moves up onto the black hole and begins to bob around as if it were orbiting the black hole, all while having swathes of mass eaten with each pass, which is much more creepy. As the Earth is eaten up from the inside, it collapses into a scattered disk of hot rock surrounding the black hole in a tight orbit. The black hole slowly doubles its mass by the time it's done feeding. The Moon's orbit is now highly elliptical. The effects on the solar system are awesome. In the biblical sense of awesome, which means terrifying. Tidal forces from the black hole would probably disrupt the near-Earth asteroids, maybe even parts of the asteroid belt, sending rocks careening through the solar system. Bombardment and impacts may become commonplace for the next few million years. The planets are slightly perturbed, but stay approximately in the same orbit. The black hole we used to call Earth will now continue on orbiting the Sun in the Earth's place. In this case, you also die. The solar system. Our home in space. We live in a peaceful part of the Milky Way. Our home is the solar system, a 4.5 billion-year-old formation that races around the galactic center at 200,000 kilometers per hour and circles it once every 250 million years. Our star, the Sun, is at the center of the solar system. It's orbited by 8 planets, trillions of asteroids and comets, and a few dwarf planets. The 8 planets are divided into 4 planets like ours: Mercury, Venus, Earth, and Mars, and 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. Mercury is the smallest and lightest of all the planets. A Mercury year is shorter than a Mercury day, which leads to enormous fluctuations in temperature. Mercury does not have an atmosphere or a moon. Venus is one of the brightest objects in the solar system and by far the hottest planet, with atmospheric pressure that is 92 times higher than on Earth. An out-of-control greenhouse effect means that Venus never cools below 437 degrees Celsius. Venus also doesn't have a moon. Earth is our home. and the only planet with temperatures that are moderate enough to allow for a surplus of liquid water. Furthermore, it's so far the only place where life is known to exist. The Earth has one moon. Mars is the second smallest planet in the solar system and hardly massive enough to keep a very thin atmosphere. Its Olympus Mons is the largest mountain in the solar system, more than 3 times as high as Mount Everest. Mars has 2 small moons. Jupiter is the largest and most massive planet in the solar system. It consists largely of hydrogen and helium and is the theatre for the largest and most powerful storms we know. Its largest storm, the Great Red Spot, is 3 times as large as Earth. Jupiter has 67 moons. Saturn is the second largest planet and possesses the smallest density of all the planets. If you had a sufficiently large bathtub, Saturn would swim in it. Saturn is also known for its extended, very visible ring system. It has 62 moons. Uranus is the 3rd largest planet and one of the coldest. Of all the gas giants, it's also the smallest. The special thing about Uranus is that its axis of rotation is tilted sideways in contrast to the 7 other planets. It has 27 moons. Neptune is the last planet in the solar system and is similar to Uranus. It's so far removed from the Sun that a Neptune year is 164 Earth years long. The highest wind speed ever measured was in a storm on Neptune at just under 2,100 kilometers per hour. Neptune has 14 moons. If we compare the sizes of the planets, the differences between them become even clearer. Jupiter is the leader in terms of size and weight. Small Mercury, on the other hand, is even smaller than one of Jupiter's moons, Ganymede. Jupiter is so massive that alone it contains roughly 70% of the mass of all the other planets and has a massive impact on its surroundings. That's a blessing for Earth, since Jupiter draws most of the dangerously large asteroids that could wipe out life on Earth. But even Jupiter is a dwarf in comparison to our star, the Sun. Calling it massive does not do justice to the Sun. It makes up 99.86% of the mass in our solar system. For the most part, it consists of hydrogen and helium. Only less than 2% is made up of heavy elements like oxygen or iron. At its core, the Sun fuses 620 million tons of hydrogen each second and generates enough energy to satisfy mankind's needs for years. But not only the 8 planets orbit our Sun. Trillions of asteroids and comets also circle it. Most of them are concentrated into 2 belts: the asteroid belt between Mars and Jupiter, and the Kuiper belt at the edge of the solar system. These belts are home to countless objects, some as large as a dust particle, others the size of dwarf planets. The most well-known object in the asteroid belt is Ceres. The most well-known objects in the Kuiper belt are Pluto, Makemake, and Haumea. Usually, we describe the asteroid belt as a dense collection of bodies that constantly collide. But in fact, the asteroids are distributed across an area that is so indescribably large that it's even difficult to see 2 asteroids at once. Despite the billions of objects in them, the asteroid belts are fairly empty places. And nonetheless, there are collisions over and over again. The mass of both belts is also unimpressive. The asteroid belt has a little less than 4% of our Moon's mass, and the Kuiper belt is only between 1/25th and 1/10th of Earth's mass. One day the solar system will cease to exist. The Sun will die, and Mercury, Venus, and maybe Earth too will be destroyed. In 500 million years, it will become hotter and hotter until at some point it will melt Earth's crust. Then the Sun will grow and either swallow Earth, or at least turn it into a sea of lava. When it has burnt up all its fuel and lost most of its mass, it will shrink to a white dwarf and burn gently for a few billion more years before it goes out entirely. Then, at the latest, life in the solar system will no longer be possible. The Milky Way will not even notice it. A small part of it in one of its arms will become just a tiny bit darker, and mankind will cease to exist, or leave the solar system in search of a new home. How big is the Moon? In the night sky, the Moon seems rather small, but in reality, it really isn't. Central Europe would easily fit under it. The surface area of the Moon is huge. To give you some perspective, it's as big as the whole European continent, China, the USA, Brazil, and South Africa together. Weight-wise, the Moon is only about 1/81th of the mass of Earth. But how big is it in relation to Earth? Quite big, actually. Our Moon is the biggest in the solar system in relation to its planet, and it's the 5th largest moon in the solar system, quite a bit bigger than the dwarf planet Pluto. Now, if the Moon is really that huge, how far away is it from us to seem this small in the night sky? 370 kilometers, as far as the ISS maybe? No, at that distance, gravitational forces would rip the Moon apart. At 36,000 kilometers, it would be as far away as our most distant satellites. Let's adjust the distance to reality. Pretty far away, right? A 747 would need 28 straight days to fly to the Moon, and even with our current technology, we'd need 2 full days. And in a car, a lot of time. So, how big is the Moon? Well, it kind of depends how you define big. But seriously though, it's pretty big. Black holes are the most powerful and extreme things in the universe, and they're wildly weird and complicated. What would happen if you fell inside one, and what are they really? First, we need to talk about space and time. Space and time are the grand stage where the play of the universe unfolds. But space isn't a fixed stage, and time doesn't tick the same for everyone everywhere. In short, they're relative. Matter bends space, and bent space tells matter how to move. Put some stars and planets on the stage, and it sags underneath them. That misshapen stage, with all its little warps and dips, gives us gravity. Black holes do not just bend the stage, they're like trapdoors. Places with so much mass that the universe formed a no-go zone where the rules change. Most black holes form when very massive stars die. We explained this process in detail in our Neutron Star video. All you need to know now is that in the final moments of really massive stars, their insides implode at nearly a quarter of the speed of light. This packs so much mass so close together, creating something so dense that it sort of breaks the stage of the universe. A black hole with 10 times the mass of the Sun would be barely 60 kilometers across. If you look directly at a black hole, it looks like nothing. The space under their control is blocked by an invisible, one-way border called the event horizon. The event horizon forms a shell around a region of space that, once entered, is shielded from the rest of the universe forever. Because the black hole trapdoor deforms space so much, not even light can escape it. And with nothing escaping to transfer information from the inside, it's impossible to tell what it really looks like. We can still observe black holes because of their effect on matter. Things can orbit black holes just as they can orbit the Sun or a planet. Many black holes have disks of matter orbiting outside the event horizon. This matter can become incredibly hot, as close orbits can speed this matter up to half the speed of light, and tiny amounts of friction and collisions between particles heat them to 1 billion degrees, making the space around these black holes, ironically, incredibly bright. What would happen if you were to try to get close or even inside a black hole? First of all, you'd see the strangest funhouse mirror in the universe. Matter isn't the only thing orbiting a black hole. Gravity is so strong near them that light can orbit too. If you hovered just outside the event horizon, at the photon sphere, in any direction, you just see yourself. Straight ahead would be the back of your own head, as light from your back travels around the black hole to your eyes. Gravity also alters the passage of time itself. The stronger the gravity, the slower time passes. While you watch the universe above you speed up, those far away will watch you in slow motion. If you chose to fly away from the black hole, you might find that eons have passed for the rest of the universe, a freakish one-way time travel trip to the future where your loved ones are long dead. But getting close to a black hole can be incredibly dangerous. A painful death by spaghettification awaits you. Because your feet are closer to the black hole than your head, they feel a stronger pull of gravity, enough to pull you apart. As you descend, it gets worse. The pulling gets stronger, your body squeezed thinner and straighter until you've been reduced to a thin stream of hot plasma, gobbled up in one final slurp, never to be seen again. Spaghettification is only a risk with smaller black holes since they have much smaller radii. If you go to the center of a galaxy and find a supermassive black hole, you might be able to experience crossing the event horizon. As you approach the event horizon, a distant observer would think they never saw you enter it, seeing you stop and fade. The last light you emit trickling up and out away from the event horizon. Meanwhile, from your perspective, the void of the black hole rises up to meet you as light from fewer directions can reach you. The blackness envelops you until your only view of the universe you left is a tiny spot of light. Here, inside the event horizon, space and time are so horribly broken that real time travel is possible, so it's probably a good thing that nothing gets out. If anything could escape, it could create all sorts of time travel paradoxes and issues that break the universe. As scary as the event horizon is, it keeps us safe from that drama. Whether you have survived this long doesn't really matter, as now there's only the certainty of crushing death in your near future. Inside the event horizon, space-time itself is so bent and warped that whatever direction you move here, every forward you go leads only towards the center of the black hole. Trying to go in any direction only brings you to the center faster. To survive the longest, you must do nothing. In the center of the black hole, we find the singularity, a single point with all the matter that has ever crossed the event horizon, all crushed to a point infinitely small. There is no memory of the things that made it, as stuff disappears down the black hole trapdoor forever. The singularity makes all things equal. This actually breaks the universe in really cool ways. We've made a video about this problem if you want to learn more. But in a nutshell, everything that comes too close becomes black hole matter concentrated at the singularity. This lack of a memory of its past means that a black hole has only three properties: its mass, spin, and electric charge. Everything else is lost. They're a lot like fundamental particles in that respect. This actually means that every single black hole in the universe is the same. Sure, their mass is different and some spin faster than others, but if we were to put all the singularities into a magical physics museum, they'd be identical, like electrons. But just like fundamental particles, the properties of singularities are the best ways we can describe them on paper, rather than an accurate representation of reality. Our current theories about the universe, namely general relativity, are just not able to describe or explain them. The curvature of space becomes infinite, density becomes infinite, and our rules just don't make sense. The singularity has no surface or size, something like a divide by zero error in the universe. So singularities might not even exist, or be completely different things. But this is all we know right now from the best prediction we have from our best current theory of space-time. Also, basically everything you've ever heard about black holes, even in this video, is about theoretical black holes that aren't spinning because their maths is so much easier. But since black holes were born from dying stars that were spinning extremely quickly in their final moments, as far as we know, all black holes in the universe should be spinning right now. At incredible speeds too, up to 90% of the speed of light. This means that in reality, black holes are even more screwed up than they usually get credit for. The singularities of rotating black holes are even wilder. The rotation causes them to swell outwards into a sort of ringularity. This rotation is so powerful that space itself is dragged along. This creates another region around spinning black holes called the ergosphere, where it's impossible to stay still no matter how hard you try. Like a rushing whirlpool of space-time, the tide is irresistible, and the black hole makes you orbit it whether you want to or not. Okay, so what will happen to black holes as the universe ages and dies around them? Again, we don't know, but we have some ideas based on our current understanding of physics. Hawking radiation. In quantum field theory, the vacuum of space is boiling with quantum fluctuations. These fluctuations are creating matter and antimatter pairs of particles from nothing which only exist for a very short time before annihilating. When this happens near the event horizon of a black hole, one of these particles can fall in, stopping them from annihilating. The escaping particle is Hawking radiation. Ultimately, the mass of this particle must come from the black hole, so over eons, black holes will shrink and radiate away. Hawking radiation is not the stuff that fell into the black hole, it's new stuff, stealing mass from it. As the black hole shrinks, the Hawking radiation gets stronger, faster and faster, until what's left eventually evaporates in a flash of high-energy radiation like a nuclear bomb. And then, nothing. But that won't happen for a long time. A black hole with the mass of our Sun has a lifetime of 10 to the power of 67 years, which means that it would take 10,000 billion years to lose 0.0000001% of its mass. But most black holes are way more massive than our Sun. The most massive supermassive black holes in the centers of galaxies have lifetimes of 10 to the power of 100 years. How long is that? Imagine an hourglass filled with 1 grain of sand for every single particle in the universe. Every 10 billion years, 1 single grain of sand falls to the bottom. If we waited for all the sand to fall down, not even 1% of the lifetimes of these black holes would have passed. There is no good concept to help our brains grasp these timescales. Will we ever truly understand black holes? Really know what's going on inside them? No one knows. We can only see their outsides, and the theories we have probably get their insides wrong. But it's okay to not know everything. It just means there's still work to be done. It means there are still mysteries to solve and big ideas to think about, which is why humans do science. In the end, we can at least be sure that we still have plenty of time left to think about them before the last one melts away. Is the universe infinite? Does it have an edge? And if so, what would you see if you went there? Today, we know that the universe had a beginning 14 billion years ago and that it's been expanding ever since. But something that's expanding should also have an edge, right? Well, it sort of does. Information can't travel faster than light. That means that we can only see parts of the universe whose light has had time to reach us in the last 14 billion years. When we look outwards, what we see is a sphere centered on us, the observable universe. But it gets a tad more complicated. Because the universe has been expanding, we know that the most faraway things whose light we can see are actually 45 billion light-years from us right now. So the observable universe is a sphere with a radius of 45 billion light-years. It contains around 200 billion galaxies, each with hundreds of billions of stars. So for us, there is an edge. We're looking at the past until there is just no past left. This edge is really more like an edge in time and, in a sense, meaningless. The real universe is for sure bigger than what we can see. But how much? There are two options. Either the universe is really big but finite, or it's truly infinite. A finite universe means that if you want to fill it with ice cream, you can do it. You need a lot of ice cream, but it is a finite amount. But that leads to a weird problem. Such a universe should have an edge, a cosmic wall where space ends. And if there's an edge, there should be something outside that edge. But the universe by definition is all there is. So how could there be stuff outside all there is? Does the idea of something outside of everything even make sense? Except, of course, there is a physics hack. You can have a universe that has no border, but that still could be filled with a finite amount of ice cream. What if the universe is truly finite? Imagine an orange and a really tiny ant. The ant can only see a small piece of the skin, just as you can only see a small chunk of the universe. But if the ant starts walking, it will eventually walk around the whole orange and be back to its starting point. So the skin of an orange is not infinite, but it doesn't have a border. The universe is not like the skin of an orange, but it could be very similar. Instead of a sphere, it could be a hypersphere, where 3D space is curled on itself, which is impossible for your brain to visualize, unfortunately. But the point is, no borders, no outside of the hypersphere. From our human ant perspective, our whole 3D space is like the peel of the orange. If you were aboard a spaceship flying in a straight line, you would eventually come back to Earth. How does any of this make sense? The actual physics is hard, so we have to simplify and lie a bit here. But in a nutshell, it all boils down to gravity. The way it works is that mass creates gravity by bending space-time. This bending is the strongest where the mass is, but sort of stretches on forever, like a very mild tension in the fabric of space-time itself. This could bend the whole universe in a way where it bends back on itself, which then makes the hypersphere. If you find this confusing, we're with you. If the universe happens to be a hypersphere, how could we find out how big it is? On Earth, we can see things disappear below the horizon, and that helps us calculate how big the Earth is. Scientists tried to find some sort of universe horizon that would reveal the scale of the cosmic sphere, but didn't see anything. Which means that if the universe is a hypersphere, it needs to be so big that from our perspective, it looks like we're living on a flat surface. For this to make sense, a hyperspherical universe should be at least 1,000 times bigger than our observable part. It could be 1 trillion times bigger for all we know, but not smaller than that. Some scientists thought all of this is way too straightforward and came up with a wilder option. The universe could be like the frosting of a donut. A hyperdonut, also impossible to visualize for your brain. This too means that if you travel in a straight line, you'd get back to where you started, but with fun complications. In a hyperdonut universe, there's not the same amount of stuff in every direction. If 2 spaceships fly in different directions, one could get back to the start way earlier. This also means that light from faraway galaxies would do fun and confusing stuff in a sort of cosmic Hall of Mirrors effect. We could see faraway things in 2 places, but not just that, we would see it in different moments in time, because its light would have taken much longer to travel in one direction than the other. You could see a star being born in front of you and see that same star die on the opposite side of the sky. How big would such a hyperdonut universe be? Well, because of its strange geometry, actually this is kind of the smallest possible universe, potentially just a few times bigger than the observable universe. But it could also be way, way bigger. We don't know. Okay, so much for finite universes. But what if it's truly infinite and space goes on forever? What would that be like? What if the universe is truly infinite? Actually, the cosmological model used by most scientists describes an infinite universe. We mostly use it to calculate what happens inside our observable chunk, but if taken literally, it predicts an infinite universe. An infinite universe goes on, well, forever, with no border anywhere, also impossible to visualize. Wherever you look, you'll find more and more stuff in every possible direction. This kind of breaks our brain a bit for a few reasons. First of all, if the universe is infinite, is it also eternal and has been there forever? Was there a time when there was nothing everywhere, and then there was something everywhere? Well, we don't know, but we have a lot of evidence for the Big Bang, so it really seems like the universe started at some point in the past. But wait, since the Big Bang, the universe has been expanding. How can an infinite thing that's everywhere become even bigger? Cosmic expansion just means that the distance between galaxies is growing with time. Even an infinite space can become bigger. Welcome to the paradoxes of infinity. Infinity gets much weirder though. As you travel with your spaceship in a straight line, you find new galaxies, stars and planets, new wonders, new weird stuff, probably new aliens and new life forms stranger than you could ever imagine. But after a long time, you might find the most special thing in the universe, yourself. An exact copy of you watching this video right now. How can that be? Well, everything in existence is made of a finite amount of different particles, and a finite number of different particles can only be combined in a finite number of ways. That number may be so large that it feels like infinity to our brains, but it's not really. If you have finite options to build things, but infinite space that is full of things in all directions forever, then it makes sense that by pure chance, there will likely be repetition. Although, just because something is possible, doesn't mean it will actually happen. Maybe the universe goes on forever, but only the boring stuff repeats itself endlessly. Maybe there is really only one you. But if the laws of physics are the same everywhere, then far, far away, gas could have given birth to stars and planets where primitive genetic information could emerge from chemistry, which might have ended up in cells and animals that evolved in really unlikely ways, and eventually apes that learn how to create online videos. It happened at least once, so the chance is not zero. Even if the chance of there being an exact copy of you watching this video right now is almost zero is still a huge number in an infinite universe. Unfortunately, you'll never meet, because almost zero still means the chance is incredibly small. Earth, as it exists right now, is so unlikely you'd have to travel incredibly far to find a second identical Earth. Some 10 to the 10 to the 29, a 1 followed by 100 octillion zeros, times the size of the observable universe, so far that it kind of means forever far away. Still, in a truly infinite universe, every combination of particles could reasonably not just occur only once, but an infinite number of times. It's time to stop now. While these scenarios are possible on paper, we've entered science philosophy here. Currently, none of these ideas are testable or provable. If the universe is infinite, we will never know. The reality is, for us, the universe is finite and has an edge. And we can see the edge in time. Everything we can interact with is within the observable universe, and most likely, this will stay true forever. Even if this finite universe feels small to you, it's more than big enough to fulfill all the dreams that we and our descendants can ever come up with. Infinitely enough for all of us. Nothing in the universe is static. In the Milky Way, billions of stars orbit the galactic center. Some, like our Sun, are pretty consistent, keeping a distance of around 30,000 light-years from the galactic center, completing an orbit every 230 million years. This dance is not an orderly ballet, more like a skating rink filled with drunk toddlers. This chaos makes the galaxy dangerous. Our solar neighborhood is constantly changing, with stars moving hundreds of kilometers every second. Only the vast distances between objects protect us from the dangers out there. But we might get unlucky in the future. At some point, we could encounter a star going supernova, or a massive object passing by and showering Earth with asteroids. If something like this were to happen, we would likely know thousands, if not millions of years in advance. But we still couldn't do much about it. Unless we move our whole solar system out of the way. To move the solar system, we need a stellar engine, a megastructure used to steer a star through the galaxy. It's the kind of thing that might be built by an advanced civilization with Dyson sphere-level technology that's thinking about their future millions of years ahead of time. But how do we possibly move the hundreds of thousands of objects in the solar system? The good news is we can ignore all of that. We only need to move the Sun. All the other stuff is glued to it by gravity and will follow it wherever it decides to go. There are lots of ideas about what a stellar engine might look like and how it would work. We've picked two grounded in our current understanding of physics that could be built in theory. The simplest kind of stellar engine is the Scariest thruster, a giant mirror. It works on the same principle as a rocket. Like rocket fuel, the photons released as solar radiation carry momentum. Not a lot, but a bit. For example, if an astronaut turned on a flashlight in space, it would push them backwards very, very slowly. A stellar engine will work a little better than a flashlight because the Sun produces a lot of photons. The basic idea of the scutoff thruster is to reflect up to half of the solar radiation to create thrust and slowly push the Sun where we want it to go. In order for the scutoff thruster to work, it must be kept in the same place, not orbiting the Sun. Although the Sun's gravity will try to pull it in, it would be supported by radiation pressure, which props the mirror up. This means the mirror would have to be very light, made of micron-thin reflecting foil from materials like aluminium alloys. The mirror's shape is important too. Enveloping the Sun in a giant spherical shell wouldn't work because that would refocus light back to the Sun, heating it up and creating all sorts of unpleasant problems. Instead, we use a parabola, which sends most of the photons around the Sun and in the same direction, which maximizes thrust. To prevent accidentally burning or freezing Earth with too much or too little sunlight, the only safe place to build a scutoff thruster is over the Sun's poles. This means we can only move the Sun vertically in the plane of the solar system and one direction in the Milky Way, which limits our travel options a bit. But that is basically it. For a civilization capable of building a Dyson sphere, this is a relatively simple endeavor. Not complicated, just very hard to build. At full throttle, the solar system could probably be moved by about 100 light-years over 230 million years. Over a few billion years, it gives us near complete control over the Sun's orbit in the galaxy. But in the short term, this might not be fast enough to dodge a deadly supernova. That's why we thought we could do better. So we asked our astrophysicist friend if he could design a faster stellar engine for this video. He did, and wrote a paper about it that's been published in a peer-reviewed journal. You can find it in our sources document. We're going to call our new stellar engine the Kaplan thruster. It works a lot like a traditional rocket. Shoot exhaust one way to push yourself the other. It's a large space station platform powered by a Dyson sphere that gathers matter from the Sun to power nuclear fusion. It shoots out a very fast jet of particles at nearly 1% the speed of light out of the solar system. A second jet pushes the Sun along like a tugboat. The Kaplan thruster requires a lot of fuel, millions of tons per second. To gather this fuel, our thruster uses very large electromagnetic fields to funnel hydrogen and helium from the solar wind into the engine. The solar wind alone doesn't provide enough fuel though, and that's where the Dyson sphere comes in. Using its power, sunlight can be refocused to the surface of the Sun. This heats small regions to extreme temperatures, lifting billions of tons of mass off the Sun. This mass can be collected and separated into hydrogen and helium. The helium is burned explosively in thermonuclear fusion reactors. A jet of radioactive oxygen at a temperature of nearly 1 billion degrees is expelled and becomes our primary source of propulsion from our stellar engine. To prevent the engine from just crashing into the Sun, it needs to balance itself. To do this, we accelerate the collected hydrogen with electromagnetic fields using particle accelerators and shoot a jet back at the Sun. This balances the thruster and transfers the thrust of our engine back to the Sun. In as little as 1 million years, this engine can move the Sun by 50 light-years, more than enough to dodge a supernova. At full throttle, the solar system can be completely redirected in its galactic orbit in 10 million years. But wait, won't we use up the Sun this way? Fortunately, the Sun is so massive that even billions of tons of material will barely scratch the surface. In fact, this megastructure will actually extend our Sun's life, since lower mass stars burn slower, keeping the solar system inhabitable for many more billions of years. With a Kaplan thruster, we could turn the entire solar system into our spaceship. For example, by orbiting backwards in the galaxy and colonizing hundreds or thousands of stars as we pass by them. It may even be possible to escape the galaxy entirely and expand beyond the Milky Way. Stellar engines are the kind of machines built by civilizations thinking not in terms of years or decades, but eons. Since we know that our Sun will die one day, a stellar engine could allow the far future descendants of humans to travel to other stars without ever having to venture into the terrifying dark abyss of interstellar space. Until we build a stellar engine, we're adrift and subject to the whims of the galactic sea. We may not like where it leads us. Maybe our descendants will set sail and become an interstellar species for millions of years to come. This was our last video for the year 12,019 of the human era. And what a year it was. So much stuff happened everywhere, to so many different people. Calendars and holidays are just imaginary, but they help us to cut our lives into pieces that our brains can handle. We're leaving 12,019 behind with a weird mixture of disillusion and hope. The world is screwed up, but we can fix it. In a few days, this year will be over, and we'll get to try again. Thank you for watching our videos, and for sticking around for so many years. See you all in 12,020. Imagine if you could gather the energy from every star within 100 million light years, from thousands of galaxies, each with billions of stars. Imagine you could take this kind of power and use it to fire the biggest superweapon in the universe. Imagine the damage you could do. It turns out, you don't need to imagine it. These exist, and they're called gamma-ray bursts. But what are these cosmic snipers? And what happens if one takes a shot at Earth? To understand gamma-ray bursts, we first have to understand gamma rays. Gamma rays are electromagnetic radiation, waves which carry energy just like visible light. Visible light is a tiny part of the electromagnetic spectrum. It's the part your eyes can see. At lower energies, there are radio waves, microwaves, and infrared. And at higher energies, ultraviolet, X-rays, and gamma rays. Gamma rays are incredibly powerful. A single gamma ray photon is more energetic than 1 million visible photons combined. Their high energy makes gamma rays a form of ionizing radiation, meaning they are energetic enough to break apart atomic bonds. This makes them dangerous to you and me. Ionizing radiation disrupts the delicate biochemical machinery that keeps us alive like a 9mm bullet through a clock. Fortunately, on Earth, the ozone layer blocks gamma rays, filtering them out before they can harm us. But if the atmosphere blocks gamma rays from space, how were gamma ray bursts, or GRBs, from space ever discovered? During the Cold War, the USA sent up spy satellites which could detect gamma rays from Soviet nuclear tests in space. They didn't see any bombs, but they did observe faint bursts coming from space, lasting only a few seconds. To date, this may be the only major scientific discovery made by spy satellites, that we know about anyway. Astronomers use telescopes that see different kinds of light to make their discoveries, and these spy satellites gave them a new pair of eyes. They were a mystery for 30 years, but eventually we discovered the source of a GRB, a galaxy 6 billion light-years away. If a GRB can be seen from such a distance, then it must be incredibly energetic, releasing more energy in a second than the Sun will in its entire 10 billion year lifetime, making GRBs the brightest events in the universe. So, where do they come from? GRBs accompany some of the most violent cataclysmic deaths in the universe and the birth of black holes. There are two types of gamma-ray burst, short and long, and each has their own source. Long GRBs last about a minute, and scientists think they are produced by supernova, when the core of a massive star collapses to become a black hole. Short GRBs last a second and are produced when two neutron stars in a binary merge. Over millions of years, their orbits decay by emitting gravitational waves. Once they're close enough to touch, they crash and splash into each other, forming a black hole. Both supernova and neutron star mergers make the same thing: black holes surrounded by a magnetized disk of gas left over from their parent stars. In these environments, the rotation winds up the magnetic field, which funnels hot jets of particles traveling at nearly the speed of light. The gas in this funnel creates two tight jets of high-energy gamma rays, like a celestial laser gun, so unlike other cosmic explosions which spread out and fade, GRBs stay focused and can be seen from much further. Any more detail would require too much mathematics for a YouTube video. The universe is full of these cosmic snipers, firing blindly and randomly into the dark, and they're hitting us all the time. On average, we detect one per day. Fortunately, most are harmless. All the bursts we have detected so far originated outside the Milky Way, too far away to hurt us. But a nearby GRB could be disastrous. If one goes off within a few light years of us, it would totally cook the surface of the Earth, or at least the half that's facing it. But even a more distant GRB could still end life on Earth. And it wouldn't need to score a headshot to kill us. If originating from a few thousand light years away, it would be 100 light years wide by the time it reaches us, washing over the solar system like a tidal wave. Again, the ozone layer protects us, but it's better equipped to handle the trickle of ultraviolet from the sun. A gamma-ray burst would overwhelm it, leaving us exposed to deadly solar radiation. Ozone takes years to replenish itself by natural processes, which is more than enough time for the sun to burn the Earth sterile, or at least to kill most complex life. In fact, this may have already happened. A GRB has been suggested as one possible cause of the Ordovician extinction 450 million years ago that eradicated almost 85% of all marine species, although it's pretty much impossible to prove. Gamma-ray bursts could even be one reason we don't see life anywhere else in the universe. They might be wiping clean huge chunks of it on a regular basis. It's been suggested that because of GRBs, only 10% of all galaxies might be hospitable to life similar to us. So, are they going to kill us? Probably not. In a galaxy like ours, there may only be one GRB per millennia, and to harm us, they must be close and directed at us. But since gamma rays travel at the speed of light, we won't know one is headed our way until it arrives, so there could already be a GRB on its way to kill us all, and we won't know it until it hits us, and we're dead. Here in the Kurzgesagt labs, we test very important ideas to see what happens when you blow things up or play with black holes. Many of you suggested that we look into an idea that sounds reasonable: shooting nuclear waste into space. It's one of those concepts that seems like an easy fix for one of the main problems with nuclear energy. But it turns out this idea is not just bad, but horribly bad, and it gets worse the longer you think about it. Why is that? What is nuclear waste? Nuclear waste is a fuzzy term and comes in categories which vary from country to country. But in general, there are three broad levels. 90% is low-level nuclear waste, tools, gloves, or trash used at a nuclear facility that could be weakly contaminated with some short-lived radioactivity. This stuff is generally safe for normal disposal. 7% is intermediate-level nuclear waste, mostly materials that have been in close proximity to a reactor core long enough to become dangerously radioactive. With proper handling, it's either safely buried or melted down and mixed into glass or concrete and stored deep underground. So 97% of nuclear waste is similar to toxic byproducts from other industries. Not great, not terrible. We can handle it. The remaining 3% is where our problems begin. High-level nuclear waste is very concentrated spent fuel taken out of a reactor core. Formerly uranium, it's now made of various dangerous and often highly radioactive elements. As a bonus, it's also incredibly hot and not easy to handle at all. This is what we want to shoot into space. All in all, around 440 active nuclear reactors create about 11,000 tons of high-level nuclear waste each year. Since 1954, we've accumulated 400,000 tons of dangerous radioactive waste. Most countries are dealing with it by not dealing with it and kicking the can towards the future. Great, so let's launch it into space. According to scientists, space is big, and nobody lives there, so it seems perfect for yeeting away this mess. There are a few tiny problems though. Problem 1, stuff ain't cheap. Even though spaceflight is getting more affordable, it's still extremely expensive. Just to get something into low Earth orbit costs on average about $4,000 per kilogram. Putting that into perspective, it costs about $1,600 to mine, separate and fabricate 1 kilogram of nuclear fuel, so launching waste into space has suddenly made nuclear fuel for reactors way more expensive and greatly increased the cost of the electricity they produce. To launch one reactor's worth of nuclear waste would cost at least $100 million per year. To deal with all the 440 operational nuclear power plants' high-level nuclear waste would cost some $44 billion per year for space launch before packaging, transport and security costs are added. Okay, let's pretend we don't care. Currently, we couldn't shoot all the nuclear waste into space even if we wanted to. There just aren't enough rockets. In 2021, we saw a record 135 launches into space. If we repurposed each of those rockets and filled them all with nuclear waste, the total amount that could be lifted into a low Earth orbit, which is the closest orbit above the atmosphere, is nearly 800 tons. We'd need at least 14 times more rockets to handle just today's nuclear waste, let alone get rid of the hundreds of thousands of tons in temporary storage. We would need to create entire new space industries to keep up with the demand for giant, toxic space trash trucks. And it gets worse. Problem 2. Space is hard. We only made the calculation for low Earth orbit, where we send most of our rockets and satellites. Littering the space around Earth with thousands of casks of spent nuclear fuel would be a nightmare for space junk management and satellite collision avoidance. Worse still, at this altitude, there's still a little bit of atmosphere causing a tiny bit of drag, so we might have nuclear waste raining down from space within just a few years. Experts would call this a huge problem. Clearly, we have to launch our waste further. If we wanted to send it to, perhaps, the Moon, we either need way more rockets or we need to build much bigger ones, making it even more expensive. A single Saturn V, the rocket used by the Apollo program, which cost around $1.5 billion adjusted for inflation per launch, could get about 43.5 tons from the Earth to the Moon. So we'd need about 260 Saturn V rocket launches every year. And of course, using the Moon as target practice for nuclear waste-tipped rockets kind of makes a huge mess. So maybe don't aim for anything. Space is empty. Do we really need a target? Shooting waste in any random direction is, you guessed it, also a bad idea. Orbits are loops, which means they have a tendency to come back to where they started. Put enough in the sky in random directions, and you'll get one back eventually. So we'd want to launch our nuclear waste deep into space, which means we need even bigger rockets that would be even more expensive. Not that we would be completely safe then. Earth might run into these interplanetary caskets at some time in the far future and experience a pretty meteor shower made from radioactive dust. Okay, how about we shoot it into the Sun? Ironically, the Sun is pretty hard to hit. While the Sun has very strong gravity, everything on Earth is moving with respect to the Sun, including the rockets that we launch, meaning a rocket would have to cancel out all the orbital motion it has around the Sun so it can stop orbiting and fall in. Because of this, it's actually easier to launch a rocket entirely out of the solar system than it is to launch it into the Sun. But to do either of these things, we need even bigger rockets, probably the biggest we've ever built. Nothing works. The thing is, it gets even worse. Problem 3. Rockets go brrrr. Rocket engineering has taken huge steps since the Apollo era. We've made them relatively safe. We've mostly replaced the toxic explosive cancer fuels of the past decades with much saner mixes of liquid oxygen and hydrogen or kerosene. The newest designs even land themselves so that they can be reused. And yet, out of the 146 launches in 2021, there were 11 failures, which means that a sizable number of our rockets carrying high-level radioactive waste would be exploding on the launch pad, or in the worst case, disassembling at high altitude or crashing from hypersonic speeds. Each failure would be at least equivalent to a mini Chernobyl, but instead of being contained under a slab of concrete, spread throughout the atmosphere. Radioactive particles could make their way to faraway places by riding on the winds. Most would fall into the ocean, but some would land on the inhabited parts of the world. They could cover farmlands and get concentrated into our food or enter our water supply, which is, well, bad. Imagine regular large-scale nuclear disasters happening. People wouldn't be happy. Conclusion and opinion part. Nuclear waste is scary, but the fear of it and horrible ideas like shooting it into space reveals how bad we are at understanding risk. because the largest amounts of radioactive elements like uranium and radon are actually released by coal. Burning millions of tons of coal each year leaves ash as a waste product that includes about 36,000 tons of radioactive materials. Less radioactive than high-level nuclear waste, but there's also a lot more of it, and it's handled way less carefully. Some of this ash is caught by filters, but most is simply pushed back into leaky mines, shoved into piles exposed to the wind, or poured into ponds that regularly spill into rivers and lakes. Living within 1.6 kilometers of an ash pile increases your cancer risk up to 2,000 times over the acceptable limit. And this is on top of other toxic chemicals like heavy metals and, of course, their massive CO2 emissions. And yet, while nuclear energy is flawed and its current form may only be a transitory technology, nuclear power plants are a harder sell than coal. Nuclear waste and the lack of willingness to deal with it are a real issue. It's not insurmountable, though. There are good methods to handle it, like burying it deep underground or reprocessing some of it into new fuel. But however we ultimately deal with this issue, we hope one thing is clear. Shooting nuclear waste into space is one of the worst ideas ever. Neutron stars are one of the most extreme things in the universe. They're like giant atom cores, kilometers in diameter, unbelievably dense and violent. But how can something like this even exist? The life of a star is dominated by two forces being in balance: its own gravity and the radiation pressure of its fusion reaction. In the core of stars, hydrogen is fused into helium. Eventually, the hydrogen in the core is exhausted. If the star is massive enough, helium is now fused into carbon. The cores of these massive stars become layered like onions as heavier and heavier atomic nuclei build up at the center. Carbon is fused into neon, which leads to oxygen, which leads to silicon. Eventually, the fusion reaction hits iron, which cannot fuse into another element. When the fusion stops, the radiation pressure drops rapidly. The star is no longer in balance, and if its core mass exceeds about 1.4 solar masses, a catastrophic collapse takes place. The outer part of the core reaches velocities of up to 70,000 kilometers a second as it collapses towards the center of the star. Now, only the fundamental forces inside an atom are left to fight the gravitational collapse. The quantum mechanical repulsion of electrons is overcome, and electrons and protons fuse into neutrons packed as densely as an atomic nucleus. The outer layers of the star are catapulted into space in a violent supernova explosion. So, now we have a neutron star. Its mass is between 1 and 3 suns, but compressed to an object about 25 kilometers wide, and 500,000 times the mass of Earth in this tiny ball that's roughly the diameter of Manhattan. It's so dense that 1 cubic centimeter of neutron star contains the same mass as an iron cube 700 meters across. That's roughly 1 billion tons, as massive as Mount Everest, in a space the size of a sugar cube. Neutron star gravity is pretty impressive too. If you were to drop an object from 1 meter over the surface, it would hit the star in 1 microsecond and accelerate up to 7.2 million kilometers per hour. The surface is super flat, with irregularities of 5 millimeters maximum, with a super thin atmosphere of hot plasma. The surface temperature is about 1 million Kelvin, compared to 5,800 Kelvin for our Sun. Let's look inside the neutron star. The crust is extremely hard and is most likely made of an iron atom nuclei lattice with a sea of electrons flowing through them. The closer we get to the core, the more neutrons and fewer protons we see, until there's just an incredibly dense soup of indistinguishable neutrons. The cores of neutron stars are very, very weird. We're not sure what their properties are, but our closest guess is superfluid neutron degenerate matter or some kind of ultra-dense quark matter called quark-gluon plasma that doesn't make any sense in the traditional way and can only exist in such an ultra-extreme environment. In many ways, a neutron star is similar to a giant atom core. The most important difference is that atom cores are held together by strong interaction and neutron stars by gravity. As if all this wasn't extreme enough, let's take a look at a few other properties. Neutron stars spin very, very fast, young ones several times per second. And if there's a poor star nearby to feed the neutron star, it can rotate up to several hundred times per second. Like the object PSR J17482446 AD. It spins at approximately 252 million kilometers per hour. This is so fast that the star has a rather strange shape. We call these objects pulsars because they emit a strong radio signal. And the magnetic field of a neutron star is roughly 1 trillion times stronger than the magnetic field of Earth, so strong that atoms get bent when they enter its influence. Okay, I think we got the point across. Neutron stars are some of the most extreme, but also some of the coolest objects in the universe. Hopefully, we'll one day send spaceships to learn more about them and take some neat pictures. But we shouldn't get too close. From hostile deserts to lonely islands and the highest mountains, wherever there is space to expand into, humans do so. So it's hardly surprising that we're already making preparations to set foot on Mars and to create the first permanent colony outside of Earth, maybe even terraform another planet and turn it into a second blue home. But wait, before we can get to the nice future stuff, we first have to complete the second phase of colonization, creating a semi-permanent outpost to prepare the ground for a larger human presence. But doing so will be gruesome. Even for an expansionist species like us, Mars is extreme. At first glance, Mars seems familiar. Polar ice caps, large valleys, liquid water under its surface, and a day barely longer than Earth's. The ideal place for us to go. Unfortunately, Mars is actually a cold, radioactive desert where the ground is poisonous and breathing is impossible. Mars is awful. You almost certainly don't want to go there. The pioneers doing the hard work on Mars will have an intensely stressful life filled with incredibly challenging problems never encountered before. But there are plenty of people willing to do that work, and we have the technology to enable them to do it. For this video, we will assume there have been prior missions to Mars to scout out a good place for an outpost, store resources and equipment, and that there's already a moon base that serves as a hub for Mars missions. The first major challenge for our outpost is the fact that Mars is very energy poor. Because of its distance from the Sun, solar power is only 40% as effective as on Earth. But even this weakened sunlight is often obscured for days by enormous dust storms. Solar power alone will probably not be enough. Alternatives such as wind power and geothermal energy are also unfeasible, as there's hardly any atmosphere and Mars's interior is much too cold. Initially, nuclear technology might be the only option. Since Mars doesn't have easily accessible radioactive elements, the nuclear fuel needs to come from Earth along with the reactor. If we do set it up, it could power our small outpost for the first few years. Unfortunately, all that energy won't be very useful if we can't breathe. Mars's atmosphere is only 1% as dense as Earth's and mostly made up of CO2. So our habitats need to be pressurized and filled with an artificial atmosphere made of nitrogen and oxygen, which comes with more problems. Corners and flat walls are weak points, so the habitats will have rounded and smooth shapes to handle the stress of great pressure differences between the interior and exterior. The airlocks need to be very airtight and work perfectly every time. Without an extensive magnetosphere or a dense atmosphere, half of all radiation coming from space reaches the ground. A person on the surface would be subjected to 50 times the radiation that they would be on Earth. 3 years on the surface of Mars exceeds the radiation dose limits imposed on NASA astronauts for their entire career. This increases cancer risks significantly. To prevent that, we could shield our habitats with a thick layer of frozen CO2 that can be harvested directly from the atmosphere. Covering the dry ice with a meter of dirt would further increase the level of protection. Sadly, this means almost no windows. From the inside, most living spaces will be windowless tunnels. From the outside, they'll look like burial mounds. All of this would still not hold back all the radiation, but reduce it just enough to be survivable for long periods of time. It won't, however, protect anyone who ventures outside. So remote-controlled robots will be used for routine work on the surface while our crew stays inside. Staying inside is a good idea for another reason: Mars dust. It's much finer than dust on Earth, so it could find its way into the gears or electronics of our machines. Because it's also very dry, it's electrostatically charged, sticking to everything, like spacesuits. It would be impossible to avoid carrying lots of Mars dust into our habitat and into the lungs of our crew. To make this even worse, Mars's soil is filled with very toxic perchlorate salts. Constant exposure could be deadly. This problem can still be overcome though. Spacesuits, for example, could be made in a way that they never truly enter the base but stay attached to the outside of the habitats. Okay, great. Now we've safely isolated humans in terms of energy and air and protected them from cancer, we just need to feed them. Water is easy to come by if a settlement is positioned near the Martian poles with their thick layers of ice. Growing food is a different kind of challenge though. Mars's soils are alkaline and lack the vital nitrogen compounds that plants need to grow. Before we can grow anything, we will have to decontaminate the soil, which is difficult and expensive. Then the soil can be fertilized using recycled biological waste. All of this will take a lot of time and is very energy intensive. So we might use aquaponics to raise fish and plants together, making the astronauts' diets more varied and tasty at the same time. This will be an important psychological boost for our overworked crew. All of these things don't solve one fundamental problem though. Mars has only 38% of Earth's surface gravity, which could cause muscle wasting, bone loss, and cardiovascular problems. While this might be solved in the future by setting up rotating living spaces, for now our crew has to live with low gravity and exercise a lot to slow the degradation down. The crews will probably have to rotate every few years. After being stuck indoors in tight spaces without windows, with the same people, performing the same routines day in, day out, with little contact from the outside world and a lot to worry about. Like Antarctic scientists or submarine staff, they will undergo intense psychological screening to make sure they're mentally resilient enough to handle this lifestyle for several years. Establishing the first real infrastructure on Mars will be extremely taxing work that only a group of very determined and competent people can do. Luckily, we have enough of these on Earth. And there you have it, a small Mars base that will survive for at least a few decades, as long as it's getting a constant supply of resources, parts, nuclear fuel, and crews from Earth. Unfortunately, Mars and Earth are separated by millions of kilometers and orbital periods that leave only a narrow travel window every 2 years. If there's an emergency in the colony, Earth wouldn't be able to help until the next travel window opens. Helpers may arrive on a planet filled with corpses. Settling Mars will be the toughest challenge we have ever faced. It will be gruesome work to establish the infrastructure we need. But we're stubborn and we like extreme challenges. If we push through Phase 2 of colonization, anything is possible. Cities illuminating the dark Martian night, a hub for travel between the planets, industries setting foot in orbit, terraforming, a true multi-planetary future. Going to Mars is hard, but worth it. And if we're lucky, we might be around long enough to see it happening and cheer on the people who take on these challenges for the benefit of us all. Are you alone in the universe? Or are you connected to anything? First of all, you're part of a group of mammals that's still very young, but we can make YouTube videos already and build large hadron colliders. We've also split the atom and invented Pokemon. We stem from an ancient life form that began living about 3.5 billion years ago. We feel like we're in control of this planet, but we aren't really. One little asteroid or one creative virus is really all it would take to kill us off for good. Humanity credits itself with being able to destroy the planet, but even with all our nuclear toys, we would probably just cause a huge mass extinction at best. Maybe we could kill 90% of everything living on this planet. Big deal. A few million years later, life would be back everywhere. Most microscopic life and life below the surface wouldn't even be disturbed that much probably. On a geological timescale, our impact on Earth is kind of laughable. We're actually not that powerful. We live on this tiny wet rock that speeds through space following a massive ball of burning plasma. One day, this ball of plasma will stop burning and most likely kill us in the process. If we survive the death of the Sun and colonize the galaxy, theoretically, we could survive until the last star in the universe goes out. After that, life becomes pretty impossible. Okay, so everything has an end. Where does this leave you as an individual? At one point in your life, for about half an hour, you were only one single cell inside your mother's womb, a creature just 0.1 millimeters in diameter. Today, you consist of about 50 trillion cells. 50 trillion incredibly complex little biological machines that are much bigger and more complex than the average bacteria. They operate by the laws of physics and chemistry and use micro-machines to build proteins, make energy usable, devour food, transport resources, transmit information, or reproduce. They communicate, duplicate, commit suicide, fight off intruders, and fulfill super specialized duties for the greater good of keeping you alive, so you can have babies. But where is the you part in this if you're made of trillions of little things? The basic information for you is stored in the DNA, a molecule that encodes the genetic instructions used in the development and functioning of all known living things. If you were to unravel it, it would be 2 meters long. If you combined all the little DNA strings in all your cells, you'd get a string so long that it would stretch to Pluto and back to Earth. That's pretty long. And your DNA is a direct connection to your very first ancestor. Take a second to think about this. In every cell of your body, there's a little string of stuff that's been there in various forms for 3.4 billion years. It evolved, it mutated, it duplicated trillions of times, but it directly connects you to the first living being on this planet. We could say you touched every living being that came before you with your DNA. But you are more than your DNA. Your body is made of 7 octillion atoms. That's 7 billion billions. Roughly 93% of the mass of the human body is made up of just 3 elements: oxygen, carbon, and hydrogen. Oxygen and hydrogen are predominantly found in water, which makes up about 60% of the body by weight. Carbon is maybe the most important element for life. It can easily bond with other atoms, which allows for the building of long, complex chains of molecules which make up the solid part of you. The remaining 7% is a tour of the periodic table of elements. Nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iron, fluorine, zinc, copper, iodine, selenium, chromium, manganese, molybdenum, cobalt, lithium, strontium, aluminium, silicon, lead, vanadium, arsenic, and bromine. Whew. By the way, this also means you're about 0.5% metal, no matter what your favorite music is. Anyway, these elements perform various functions like enabling oxygen transport, building of bones and cell structures, carrying signals, driving chemical reactions, and a lot more. Your body is in a constant state of transition. Every 16 days, 75% of you has been replaced because a healthy human exchanges about 100% of their water in that time period. Each year, about 98% of your atoms are replaced by new ones, and every 5 years, close to all of the atoms that make up your body weren't there 5 years ago. So, you could call yourself a temporary collection of atoms. But where did these atoms come from? In the beginning of the universe, there were mostly hydrogen and helium atoms. Enormous gas clouds formed over millennia and grew denser and denser until they collapsed under their own gravity, giving birth to the first stars. In the cores of these stars, hydrogen was converted into helium under extreme conditions. After millions of years, the hydrogen became exhausted and the stars began dying. Under super extreme conditions, all elements we know today were created a fraction of a second before they died and exploded in supernovas. They shot most of their contents into space, while the cores collapsed and became black holes. All these elements traveled through space for who knows how long, until they arrived at a different cloud that was slowly forming a new star, our Sun. These elements that once were the insides of a star formed planets and found their way onto Earth, where they enabled life to begin. So we are directly connected to the first stars ever born in the universe. We are part of the universe. The idea of being a deeply connected, minuscule part of an enormous structure is really mind-blowing. We don't know what all this means, or if it means anything at all. We know that we're made of little parts that connect us to everything in the universe, to the beginning of everything. And this is kind of a nice thought. You are not alone. You never were. You never will be. If you saw a wormhole in reality, it would appear round, spherical, a bit like a black hole. Light from the other side passes through and gives you a window to a faraway place. Once crossed, the other side comes fully into view, with your old home now receding into that shimmering spherical window. But are wormholes real, or are they just magic disguised as physics and maths? If they are real, how do they work, and where can we find them? For most of human history, we thought space was pretty simple, a big flat stage where the events of the universe unfold. Even if you take down the set of planets and stars, there's still something left. That empty stage is space, and it exists, unchanging and eternal. Einstein's theory of relativity changed that. It says that space and time make up that stage together, and they aren't the same everywhere. The things on the stage can affect the stage itself, stretching and warping it. If the old stage was like unmoving hardwood, Einstein's stage is more like a waterbed. This kind of elastic space can be bent and maybe even torn and patched together, which could make wormholes possible. Let's see what that would look like in 2D. Our universe is like a big flat sheet. Bent in just the right way, wormholes could connect two very, very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. So, where can we find a wormhole? Presently, only on paper. General relativity says they might be possible, but that doesn't mean they have to exist. General relativity is a mathematical theory. It's a set of equations that have many possible answers, but not all maths describes reality. But they are theoretically possible, and there are different kinds. The first kind of wormholes to be theorized were Einstein-Rosen bridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat, but curved by objects on it. If we compress that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. A one-way barrier forms, the event horizon, which anything can enter, but nothing can escape, trapped forever at the singularity at its core. But maybe there is no singularity here. One possibility is that the other side of the event horizon looks a bit like our universe again, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole. In the parallel universe with backwards time, the mirror black hole is spewing things out a bit like a Big Bang. This is called a white hole. Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite universe, and they crimp shut in the middle. If you go into a black hole, you won't become the stuff coming out of the white hole. You'll only become dead. So, to travel the cosmos in the blink of an eye, humans need a different kind of wormhole, a traversable wormhole. If string theory, or one of its variations, is the correct description of our universe, then we could be lucky and our universe might even have a tangled web of countless wormholes already. Shortly after the Big Bang, quantum fluctuations in the universe at the smallest scales, far, far smaller than an atom, may have created many, many traversable wormholes. Threaded through them are strings, called cosmic strings. In the first billionth of a trillionth of a second after the Big Bang, the ends of these tiny, tiny wormholes were pulled light years apart, scattering them through the universe. If wormholes were made in the early universe, whether with cosmic strings or some other way, they could be all over, just waiting to be discovered. One might even be closer than we realize. From the outside, black holes and wormholes can look very similar, leading some physicists to suggest the supermassive black holes in the center of galaxies are actually wormholes. It will be very hard to go all the way to the center of the Milky Way to find out though, but that's okay. There might be an equally extremely hard way to get our hands on a wormhole. We could try to make one. To be traversable and useful, there are a few properties we want a wormhole to have. First, it must obviously connect two distant parts of space-time, like your bedroom and the bathroom, or Earth and Jupiter. Second, it should not contain any event horizons which would block two-way travel. Third, it should be sufficiently sized so that the gravitational forces don't kill human travelers. The biggest problem we have to solve is keeping our wormholes open. No matter how we make wormholes, gravity tries to close them. Gravity wants to pinch it closed and cut the bridge, leaving only black holes at the ends. Whether it's a traversable wormhole with both ends in ours, or a wormhole to another universe, it will try to close unless we have something propping it open. For very old string theory wormholes, that's the cosmic strings job. For man-made wormholes, we need a new ingredient: exotic matter. This isn't anything like we find on Earth or even antimatter. It's something totally new and different and exciting with crazy properties like nothing that's ever been seen before. Exotic matter is stuff that has negative mass. Positive mass, like people and planets and everything else in the universe, is attractive because of gravity. But negative mass would be repulsive. It would push you away. This makes a kind of anti-gravity that props open our wormholes. And exotic matter must exert enormous pressure to push space-time open, greater even than the pressure at the centers of neutron stars. With exotic matter, we could weave space-time however we see fit. We may even have a candidate for this exotic matter, the vacuum of space itself. Quantum fluctuations in empty space are constantly creating pairs of particles and antiparticles, only for them to be annihilated an instant later. The vacuum of space is boiling with them, and we can already manipulate them to produce an effect similar to the negative mass we're looking for. We could use this to stabilize our wormholes. Once we're keeping it open, the ends would start together, so we'd have to move them around to interesting places. We could start by wiring the solar system, leaving one end of each wormhole in orbit around the Earth. We could fling others into deep space. The Earth could be a wormhole hub for a vast interstellar human civilization spread over light years, but only a wormhole away. However, wormholes have a dark side. Even opening a single wormhole kind of breaks the universe in fundamental ways, potentially creating time travel paradoxes and violating the causal structure of the universe. Many scientists think that this not only means they should be impossible to make, but that it's impossible for them to exist at all. So for now, we only know that wormholes exist in our hearts and on paper in the form of equations. What is the largest star in the universe? And why is it that large? And what are stars anyway? Things that would like to be stars. We begin our journey with Earth, not to learn anything, just to get a vague sense of scale. The smallest things that have some star-like properties are large gas giants or sub-brown dwarfs, like Jupiter, the most massive planet in the solar system, 11 times larger and 317 times more massive than Earth, and more or less made of the same stuff as our Sun, just much less of it. The transition towards stars begins with brown dwarfs, failed stars that are a huge disappointment to their mums. They have between 13 and 90 times the mass of Jupiter. So even if we took 90 Jupiters and threw them at each other, although fun to watch, it wouldn't be enough to create a star. Interestingly, adding lots of mass to a brown dwarf doesn't make it much bigger, just its insides denser. This increases the pressure in the core enough to make certain nuclear fusion reactions happen slowly and the object glow a little. So brown dwarfs are a sort of glowy gas giant that don't fit into any category very well. But we want to talk about stars, not failed wannabe stars, so let's move on. Main sequence stars. Once large gas balls pass a certain mass threshold, their cores become hot and dense enough to ignite. Hydrogen is fused to helium in their cores, releasing tremendous amounts of energy. Stars that do that are called main sequence stars. The more massive a main sequence star is, the hotter and brighter it burns, and the shorter its life is. Once the hydrogen burning phase is over, stars grow, up to hundreds of thousands of times their original size. But these giant phases only last for a fraction of their lifespan. So we'll be comparing stars at drastically different stages in their lives. This doesn't make them less impressive, but maybe it's good to keep in mind that we'll be comparing babies to adults. Now back to the beginning. The smallest real stars are red dwarfs, about 100 times the mass of Jupiter, barely massive enough to fuse hydrogen to helium. Because they are not very massive, they are small, not very hot, and shine pretty dimly. They are the only stars in the main sequence that don't grow once they die, but sort of fizzle out. Red dwarfs are by far the most abundant type in the universe. Because they burn their fuel very slowly, it lasts them up to 10 trillion years, 1,000 times the current age of the universe. For example, one of the closest stars to Earth is a red dwarf star, Barnard's star, but it shines too dimly to be seen without a telescope. We made a whole video on red dwarfs if you want to learn more. The next stage are stars like our Sun. To say the Sun dominates the solar system is not doing it justice, since it makes up 99.86% of all its mass. It burns far hotter and brighter than red dwarfs, which reduces its lifetime to about 10 billion years. The Sun is 7 times more massive than Barnard's star, but that makes it nearly 300 times brighter with twice its surface temperature. Let's go bigger. Small changes in mass produce enormous changes in a main sequence star's brightness. The brightest star in the night sky, Sirius, is 2 solar masses with a radius 1.7 times that of the Sun, but its surface is nearly 10,000 degrees Celsius, making it shine 25 times brighter. Burning that hot reduces its total lifespan by 4 times to 2.5 billion years. Stars close to 10 times the mass of our Sun have surface temperatures near 25,000 degrees Celsius. Beta Centauri contains 2 of these massive stars, each shining with about 20,000 times the power of the Sun. That's a lot of power coming from something only 13 times larger, but they'll only burn for about 20 million years. Entire generations of these blue stars die in the time it takes the Sun to orbit the galaxy once. So is this the formula? The more massive, the larger the star. The most massive star that we know is R136A1. It has 315 solar masses and is nearly 9 million times brighter than the Sun. And yet, despite its tremendous mass and power, it's barely 30 times the size of the Sun. The star is so extreme and barely held together by gravity that it loses 321,000 billion tons of material through its stellar wind every single second. Stars of this sort are extremely rare because they break the rules of star formation a tiny bit. When supermassive stars are born, they burn extremely hot and bright, and this blows away any extra gas that could make them more massive. So the mass limit for such a star is around 150 times the Sun. Stars like R136A1 are probably formed through the merger of several high-mass stars in dense star-forming regions and burn their core hydrogen in only a few million years. So this means they are rare and short-lived. From here, the trick to going bigger isn't adding more mass. To make the biggest stars, we have to kill them. Red giants. When main sequence stars begin to exhaust the hydrogen in their core, it contracts, making it hotter and denser. This leads to hotter and faster fusion, which pushes back against gravity and makes the outer layers swell in a giant phase. And these stars become truly giant indeed. For example, Galaxies. Only 30% more massive than the Sun, it has swollen to about 84 times its radius. Still, when the Sun enters the last stage of its life, it will swell and become even bigger, 200 times its current radius. In this final phase of its life, it will swallow the inner planets. And if you think that's impressive, let's finally introduce the largest stars in the universe, hypergiants. Hypergiants are the giant phase of the most massive stars in the universe. They have an enormous surface area that can radiate an insane amount of light. Being so large, they're basically blowing themselves apart, as gravity at the surface is too weak to hold on to the hot mass which is lifted away in powerful stellar winds. Pistol Star is 25 solar masses, but 300 times the radius of the Sun, a blue hypergiant aptly named for its energetic blue starlight. It's hard to say exactly how long Pistol Star will live, but probably just a few million years. Even larger than the blue hypergiants are the yellow hypergiants. The most well-studied is Rho Cassiopeia, a star so bright it can be seen with the naked eye, although it's thousands of light years from Earth. At 40 solar masses, this star is around 500 times the radius of the Sun and 500,000 times brighter. If the Earth were as close to Rho Cassiopeia as it is to the Sun, it'd be inside it and you would be very dead. Yellow hypergiants are very rare though, only 15 are known. This means they're likely just a short-lived intermediate state, as a star grows or shrinks between other phases of hypergiantness. With red hypergiants, we reach the largest stars known to us, probably the largest stars even possible. So, who's the winner of this insane contest? Well, the truth is, we don't know. Red hypergiants are extremely bright and far away, which means that even tiny uncertainties in our measurements can give us a huge margin of error for their size. Worse still, red hypergiants are solar system-sized behemoths that are blowing themselves apart, which makes them harder to measure. As we do more science and our instruments improve, whatever the largest star is will change. The star that is currently thought to be among the largest we've found is Stephenson 218. It was probably born as a main sequence star a few tens of times the mass of the Sun and has likely lost about half its mass by now. While typical red hypergiants are 1,500 times the size of the Sun, the largest rough estimate places Stephenson 218 at 2,150 solar radii and shining with almost 500,000 times the power of the Sun. By comparison, the Sun seems like a grain of dust. Our brains don't really have a way of grasping this kind of scale. Even at light speed, it would take you 8.7 hours to travel around it once. The fastest plane on Earth would take around 500 years. Dropped on the Sun, it would fill Saturn's orbit. As it evolves, it will probably shed even more mass and shrink down into another hotter hypergiant phase, accumulate heavy elements in its core before finally exploding in a core collapse supernova, giving its gas back to the galaxy. This gas will then go on to form another generation of stars of all sizes, starting the cycle of birth and death again to light up our universe. Let's make this journey again, but this time without the talking. The universe is big. There are many large things in it. If you want to play a bit more with size stuff, we have good news. We've created our first app, Universe in a Nutshell, together with Tim Urban, the brain behind Wait But Why. You can seamlessly travel from the smallest things in existence, past the coronavirus, human cells and dinosaurs, all the way to the largest stars and galaxies, and marvel at the whole observable universe. You can learn more about each object or simply enjoy the sheer scale of it all. The app is inspired by the Scale of the Universe website by the Huang twins that we spent a lot of time with when it came out years ago, and felt that it was finally time to create a Wait But Why and Kurzgesagt version. You can get it in your app store, there are no in-app purchases and no ads. All future updates are included. And since this is our first app, we'd love to hear your feedback so we can improve it over time. If this sounds good to you, download the Universe in a Nutshell app now and leave us a 5-star review if you want to support it. Kurzgesagt and all the projects we do are mostly funded by viewers like you. So if you like the app, we'll make more digital things in future. Thank you for watching. Supernovae are the most powerful explosions in the universe, unleashing enough energy to outshine galaxies. We have no real metaphor for their power. If the sun were to magically go supernova, it would feel like you were being hit by the energy of a nuclear explosion every second for weeks. While supernovae are the engines of creation, forging the elements that enable life, they also burn sterile whole regions of galaxies. So what would happen if one hit Earth? There are, roughly speaking, 2 ways to make a supernova. Either the core of a massive star implodes, or, less common, a white dwarf gains mass to the point where it ignites explosive nuclear fusion. The outcome is the same, a supernova explosion. When we think of an explosion on Earth, we think of something that happens fast and ends. But a supernova is more like a volcanic eruption followed by a tsunami. At first, there's a colorful ball of hot, expanding gas, creating a spectacular cloud that will shine for about a month. But then, it doesn't stop. Hot and dangerous gas rushes outwards at speeds of 10,000 kilometers a second through the near vacuum of space, sweeping up the sparse gas of the galaxy. This wall of gas expands for tens of thousands of years and will eventually span up to dozens of light years until it finally cools off and disperses its substance back into the galaxy. So what if this star tsunami hits us? Well, the damage depends on how far away it is. Stage 1, thousands of light years away. Humans have witnessed dozens of supernovae, but all of them were thousands of light years away. They appeared as new stars, some outshining the moon, twinkling for a few weeks and disappearing. Aside from looking very pretty at this distance, they don't do much to us. Stage 2, 300 light years away. Things begin to get a bit icky once a supernova occurs around 300 light years away. We can expect one this close to us every few million years. A single star giving the night sky an eerie glow like twilight. And while this is far enough away and dim enough to not do harm to us, they can affect the Earth. At these distances, it's like being hit by the last weak waves of the star tsunami. Not strong enough to do real damage, but still noticeable. In fact, we know that over the past 10 million years, multiple supernovae have struck Earth from these distances because we can find radioactive isotopes of iron deep in the rocks and sediments at the bottom of the ocean. Amazingly, these supernovae around the solar system have cleared a 1,000 light-year wide pocket of space that's called the local bubble. They blew away the interstellar gas and dust, creating a lumpy wall of gas that's now a cradle for star formation. Stage 3, 150 light-years away. Once a supernova happens much closer than 300 light-years, we're approaching the zone where it does real damage. Stars have extremely powerful magnetic fields. When they die, the tsunami of dead star actually retains a lot of this magnetic energy woven through the shockwave that expands outwards. In this highly magnetized cloud, we get conditions like in a huge particle accelerator that's accelerating charged particles like protons, nuclei, and electrons to immense speeds. Which means we have an expanding cloud that is shooting deadly radiation in all directions long after the bright light from the initial explosion has faded away. If a supernova happens too close by, waves of these cosmic rays will wash over the solar system for thousands of years. While we're mostly protected on Earth's surface by the atmosphere and ozone layer, the influx of extra radiation will still increase cancer and mutation rates. Not enough to cause a mass extinction, but it will be noticeable. Spaceflight would become impossible in the solar system as astronauts wouldn't survive the waves of radiation for long. We don't know exactly how bad this would be, but a supernova that is close enough may trap our species on Earth for generations, maybe thousands of years. It only gets worse from here. Stage 4, closer than 100 light-years. Within 100 light-years, things get bad as a supernova disrupts our climate in ways that we don't fully understand yet. there are a few unpleasant things happening all one after another. First, the high-energy photons arrive from the explosion, followed by many decades of radiation from the radioactive tsunami, both of which seriously damage the ozone layer, Earth's shield against harmful radiation. The ozone layer absorbs ultraviolet radiation by breaking apart ozone, O3, into O2 and a free oxygen atom, which later reforms back into another ozone molecule. But the supernova radiation breaks up nitrogen molecules that gobble up the free oxygen, breaking the cycle and depleting the ozone layer quickly. Without a radiation shield, everybody living on the surface is exposed to very high levels of UV radiation from our sun. Cancer rates would skyrocket, and just going outside during the day could be life-threatening. The extra radiation would also kill a lot, if not most, of the plankton in the oceans that live near the surface and are the basis for the marine food chains, leading to a mass extinction. Worse still, supernova radiation would ionize gas in the atmosphere, which means that it would punch through molecules and knock electrons off nuclei, leaving them charged. These charged nuclei then act as seeds for water vapor to gather and form massive global clouds. In the worst case, they would reflect enough sunlight to trigger an ice age. In fact, it's thought that the Ice Age 2.5 million years ago was caused by a supernova. Some scientists even think that a supernova about 60 light-years away might have been the cause of the Devonian mass extinction 350 million years ago. But wait, there's more. The electrons punched free by the radiation form enormous electric avalanches, or in other words, lightning. Earth is hit by some of the worst thunderstorms in millions of years. The intense lightning causes global wildfires that consume forests and crops, devastate cities, disrupt our electrical grids and global supply chains, all while a decimated ozone layer leaks deadly radiation. While in the past the ecosystem may have bounced back from a nearby supernova after a few thousand or million years, there's no guarantee modern civilization can take a hit of this magnitude. We would face food shortages, skyrocketing prices and wars as nations struggle to not be consumed by chaos. So a supernova this close would at the very least do significant damage for hundreds or thousands of years, if not end our modern civilization, and with it millions or even billions of lives. Still, humanity would likely survive and could recover. Stage 5. Closer than 25 light-years. A supernova closer than 25 light-years means that we're in its kill radius, where a mass extinction is all but guaranteed. Probably about half of the ozone layer would be destroyed, and massive climatic disruption on a scale we've never witnessed would ravage Earth. Entire ecosystems would swiftly be wiped out by radiation as global wildfires envelop the planet. All the things described before happen, but way more intensely and much faster. A few people might survive for years in bunkers if they have food supplies, but the world they return to will be devastated and hostile to life for hundreds of thousands of years. Human extinction is extremely likely. The final stage, 4 light-years. Being any closer to a supernova is very unlikely because space is big, but the effects would be extreme. Even from 4 light-years away, the distance to Alpha Centauri, a supernova would be almost as bright as the sun in the sky. While casting 2 shadows could be fun for a few hours, within days the Earth's surface gets as hot as a sauna, baking the surface for weeks until the explosion fades. The surface of Earth burns, scoured of life. Even the oceans aren't safe. The massive amount of radiation that follows burns away the ozone layer, killing everything that sees sunlight. It would be the largest extinction event in history, reducing life to a few survivors in the deep sea and critters in the deep soil. Life basically has to start over. Conclusion. How worried do you need to be? So, should you worry? No. Fortunately, there are only a handful of stars that may explode within 1,000 light-years of Earth, and none are close enough to be a serious threat. Even better, these stars will probably not go supernova for many millions of years. So you are safe. But there's no guarantee for the far future. As stars orbit the galaxy, our descendants may find themselves dangerously close to a supernova. But by then, a far more advanced and wiser humanity will hopefully be able to just move out of the way. In any case, you can sleep well tonight, under the beautiful night sky. Mars is a disappointing hellhole lacking practically everything we need to stay alive. It looks like we'll only ever have small crews spend a miserable time hidden underground. Except we could terraform it into a green new world. But to solve the planet's problems, we first need to make it worse and turn it into oceans of lava with gigantic lasers. This isn't a far-fetched science fiction tale. Terraforming Mars is possible on the kind of timescale our ancestors built great monuments in. If humanity solves some of its pressing problems and ventures into space to expand into the solar system, this may not be that far off. Okay, so how do we terraform Mars quickly? Well, it's complicated. Mars is dry and has no soil to grow anything. Its atmosphere is too thin to breathe or protect us from radiation, giving you a high risk of cancer. So to turn it into a new home for humanity, we have to give it a proper atmosphere similar to Earth's. It should be made of 21% oxygen, 79% nitrogen, and a tiny bit of CO2 at an average temperature of 14 degrees Celsius and under 1 bar of pressure. We have to create oceans and rivers, and then the ground has to be weathered into fertile soil to host living things. Then we need to install a biosphere on the surface and prevent it all from being undone by installing protective measures that can stand the test of time. It is difficult, but a big laser makes it a lot easier. Challenge 1. The atmosphere. Some 4 billion years ago, Mars had a nice oxygen-rich atmosphere and was home to vast oceans and rivers. It held onto it for several hundred million years before it got blown away. Ultraviolet rays broke down the atmospheric gases and then the oceans until they were swept away by solar wind. Today, Mars is a dry, barren wasteland. Luckily, a sizable portion of the water is frozen in deep reservoirs and in the polar ice caps, enough to create a very shallow ocean. And enormous amounts of oxygen are bound as minerals in the Martian rocks, like the oxygen in the iron oxides that give the planet its rust-red color, as well as carbon dioxide in carbonates. To free these gases, we need to reverse the reactions that lock them away by using thermolysis, which occurs at temperatures as high as on the surface of the Sun. In short, we want to melt the surface of Mars. The best way to do that would be to put lasers in orbit, aiming their beams down on Mars. The most powerful laser today is the Eli NP, able to produce beams of 10 petawatts of power for a trillionth of a second. To melt Mars, we need a laser twice as powerful that runs continuously. The easiest way is to use a solar-pumped laser that can be powered directly with sunlight. At its core are metal-infused glass rods that absorb energy and release it as a laser beam. If we build an array of mirrors in space about 11 times the size of the United States, we can focus enough sunlight onto them to melt Mars. Let's do it! As the lasers hit the surface, about 750 kilograms of oxygen and some carbon dioxide emerge from every cubic meter of rock melted. If we are efficient, our lasers only need to melt through the top 8 meters of the surface to get enough oxygen. It would look terrifying. The skies would be shrouded in storms, while the ground would glow red-hot, crisscrossed by currents of lava. Tireless laser beams sweep over the landscape, leaving trails too bright to look at. After they pass, the ground cools quickly. A strange snow falls, the ashes from all the elements that solidify as they cool down, like silicon and iron. Mars is still a cold planet at this point. A happy side effect of this inferno is that all the water in the polar ice caps and even deep underground rises into the sky as hot steam, forming clouds that rain down over the entire planet. They would wash out the nastier gases from the atmosphere like chlorine and carry away harmful elements that accumulated on the surface. In the end, they would form shallow oceans, saltier than on Earth. We might need to do an extra cleanup afterwards. It would take about 50 years of continuous lasering to create our oxygen atmosphere. We could use this opportunity to dig deeper in some places to create the basins for salty oceans or rivers and spare some landmark features like Olympus Mons and Valles Marineris. We're not done though. The resulting atmosphere is nearly 100% oxygen and only 0.2 bar. It's hard to breathe and very flammable. To make it similar to Earth and a lot safer, we need to add a lot of nitrogen, which Mars is sadly lacking. We have to import it. The ideal source is Titan, a large moon of Saturn, covered in a thick atmosphere that's almost entirely nitrogen. We just have to move 3,000 trillion tons from the outer solar system to Mars. While that's not easy, it is doable. To process that much of Titan's atmosphere, we have to construct giant automated factories on its surface powered by our lasers to suck in the atmosphere and compress it into a liquid. This gets pumped into bullet-shaped tanks, which a mass driver shoots all the way to the red planet, where they explode and mix with the oxygen. We've already been able to send individual missions to Saturn in just a few years. With enough resources, it should be possible to complete the task within 2 generations. Of course, it would be much more convenient to have nitrogen left over from terraforming Venus on the side. We explained this in detail in another video. So, about a century after the start of the terraforming process, we have a breathable atmosphere that has the right gases. If the liberated CO2 isn't enough to warm it up to temperatures we can stand, we just add some super greenhouse gases. Mars at this point resembles a black marble from all the cooling lava, spotted with growing oceans and red patches where the old surface remains untouched. It's still a wasteland, no better than a desert on Earth. We need to fill it with life. Challenge 2. Biosphere. Installing a biosphere on a new planet is very difficult. Unexpected interactions between species or sudden diseases can destabilize it to the point of collapse. We would probably begin by seeding our young oceans with phytoplankton. Without competition, it would bloom rapidly, filling up the oceans to become the bottom of an aquatic food chain. They can be followed by tiny zooplankton, then by fish, maybe even sharks and whales. If things go well, life in the oceans will thrive. Life on land is harder. Plants need nutrient-filled ground to sink their roots into, but most of the surface is the congealed remains of lava and ash. We could wait for thousands of years for water and wind to grind it down into finer sands, or try to do it manually. But we want to be quick, and we have a big laser. Turning the beam on and off in rapid succession would cause the ground to quickly heat up and contract, which breaks it into smaller and smaller pieces. Add a bit of water and you get a sort of dark mud. Into this mud, we can mix fungi and nitrogen-fixing bacteria. They're able to absorb nitrogen and convert it into nitrate compounds to feed plants. The first plants we want to bring are native to volcanic islands on Earth, since they're perfectly suited to the laser-blasted Martian landscape. Eventually, the enriched mud becomes the foundation for grasslands and forests. In Mars's lower gravity, trees can become very tall very fast. Their roots gather the nutrients they need and then dig deeper to turn more rocks into soil, forming a self-sustaining ecosystem. At this point, we can slowly introduce more plant varieties, insects, and animals. Not mosquitoes, though. The new biosphere needs to be maintained to prevent it from falling out of balance. If plants grow too quickly and absorb too much carbon dioxide, the planet cools down too much. If key species die out, we could see populations collapse faster than they could recover. On Earth, other species would move in to fill the void, but our Martian biosphere is not as flexible. It takes hundreds, if not thousands of years before Mars becomes a stable environment. But eventually, the planet will have the potential to sustain large human colonies. With air, water, and food available, we can finally call Mars, black, blue, and green, our home. A giant volcanic island in space. Will it last, though? Challenge 3. The long-term future. There is a problem we haven't addressed. Mars's core does not produce a magnetic field, so it doesn't have enough protection from solar radiation or cosmic rays. This becomes dangerous for the long-term health of Martian populations. So, as a final step, we need an artificial magnetic field. It doesn't have to be huge like Earth's, it just needs to deflect the solar wind enough so that it doesn't touch Mars. The easiest way is to construct a magnetic umbrella far ahead of Mars that splashes the solar wind to the sides. A big superconducting ring powered by nuclear facilities is all it takes. It would orbit at the Mars-Sun L1 point, keeping it constantly in between the Sun and Mars and protect the new atmosphere. And that's it. Terraforming Mars would take some work, hefty resources, and probably a century or 10, but it would be the first time we've lived in a home designed and shaped solely by us and for us. A first step towards our future among the stars. Welcome to the Kurzgesagt lab. Let's conduct a few stellar experiments. We'll first add some more mass to this protostar. More. A bit more. Wow, we've just created a blue giant, a star with 10 times the mass of our Sun. Let's now add a couple of million years and see what happens. A supernova. Breathtaking. And look, it leaves behind a black hole. Fascinating stuff. Now we record our findings. Be careful to preserve the sparkle. It's now time for Duck's final inspection. This one is always a nail-biter. He has incredibly high standards. Luckily for us, our work is scientifically accurate, offers an overview of important astrophysical processes, and is a real stunner. Duck approves. Looks like it's ready to be shared with the world as a poster. A very special piece of Kurzgesagt you can take home and touch. You can get this very special poster along with many other sciencey and spacey things created with love and care from our shop. There might be an object so indestructible, extreme and brutal that it could kill black holes. Gravastars. Cosmic soap bubbles filled with pure energy and with a shell made of the weirdest material that's possible in nature. What are they? What do they look like? And are they just a theoretical fever dream, or will they change our understanding of the universe forever? The birth of the most extreme objects in the universe. Very massive stars die in the most dramatic way possible, a supernova. We've explained this process in detail before, but in a nutshell, in less than a second, their cores collapse, crushed under their extreme gravity. The star's shell rushes in, bounces against the collapsing core, and explodes, shining brighter than whole galaxies. Depending on how massive the star was, there are two possible outcomes. Either the core compresses into a super-dense neutron star, or it kind of breaks reality and collapses into a singularity, an infinitely dense point with no size or dimensions at all. A place where the laws of the universe stop making sense and time and space are reversed. A black hole. Gravastars are a third, even weirder option. Instead of collapsing into an infinitely dense point, the core is kind of ground down, like a rock pulverized to dust by a cosmic hydraulic press. Atoms and particles are crushed so hard that they transform into pure energy. A sort of mini-universe, if you want. And just like our universe, this bubble violently wants to expand and grow. In a fraction of a second, the bubble smashes into the collapsing star around it. The unspeakable mass of the star collapsing under its own gravity meets the titanic violence of the expanding energy bubble. Like an ancient god hammering on its anvil, matter is trapped between an immovable object and an unstoppable force, forging a new kind of material that we've never seen before, but that we know is physically possible. And then it suddenly stops. A gravastar is born. What does it look like? Cosmic soap bubbles. Just like black holes, a gravastar can have any mass, but a typical one would be about the size of the London metropolitan area and as massive as 10 suns. The shell of the gravastar is utterly dark and the coldest thing in the universe, only a billionth of a degree above absolute zero. If we look at it in deep infrared, even the cosmic microwave background glows bright in comparison. How can anything made of matter be that cold? Don't all atoms jiggle back and forth? The thing is, the shell's not made out of atoms. It's made from an entirely new, unique and extreme matter that doesn't have a name yet, and that's at the very limit of what's physically possible in nature. Actually, the shell is so incredibly thin that atoms seem truly gigantic next to it. And yet, despite being ultra-thin, because it's been forged by two impossibly extreme forces, the shell is incredibly tight. So tight that if you wanted to stretch the whole shell by just 1 meter, you'd need the energy of an entire supernova. What about the inside? Well, it only gets weirder. The interior of a gravastar is perfectly simple because it's sort of empty. Completely empty. A perfect vacuum without a single atom, particle, or wave. But despite being as empty as it gets, this vacuum is boiling with the most primitive and fundamental kind of energy in the universe. We need a detour to explain how any of this makes sense. The fundamental nothingness at the core of it all. The inside of a gravastar breaks our brains a bit because it's a sort of super-condensed nothingness. What does this even mean? We'll have to simplify and use metaphors to make sense of what scientists measure and calculate. According to our current understanding of physics, particles like quarks, electrons, photons, and so on are not really solid objects, but sort of waves in an ocean. In our human world, you can't have waves without water, and in the smallest world, you also can't have particle waves without some kind of underlying, omnipresent cosmic fluid. This fluid is the vacuum, what we perceive as nothingness. It's the fundamental ocean at the bottom of reality. The waves of this vacuum ocean are the particles that make up you and everything else. But even when there are no waves or particles traveling through it, the fluid is still there, and like any fluid we know, it has inherent energy. Vacuum fluid is everywhere in the universe. The room you're in is 99.98% vacuum between the air particles bouncing around. Between the trillions of particles making up your cells, there's vacuum. But it's different inside a gravastar. When our star collapsed and condensed so violently, it was as if the universe took a cosmic pump and compressed as much vacuum fluid as physics allows, into a kind of super dense nothingness. As said before, even without any waves, the nothingness vacuum ocean of the universe has energy. But the super dense vacuum inside a gravastar has almost a billion, trillion times more energy per cubic centimeter than the vacuum outside the star. This is an unbelievable amount of energy and mass in a tiny space, just like, you may have guessed it, black holes. This intensely compressed vacuum ocean can't be compressed any further. It's at the absolute physical limit of anything that could be squeezed together without breaking physics, like black holes do. The ocean would love to stop being so tight. It wants to stretch out and flow back into the ocean that surrounds the star, but it's trapped in the safest prison possible. The shell, which itself is right at the edge of the physical limit of any material possible. An eternal stalemate between two limits of the universe. Let's leave this world of metaphors and get back to our world that feels more real. In our world, gravastars are perfectly black, eternal objects with borderline insane amounts of mass. Because they're so cold, dark, and massive, from the outside, gravastars look and behave exactly like black holes. Both massively curve space around them and create all the fun effects we love black holes for, from trapping mass and light in accretion disks or slowing down time as you get closer. For details, we've made 1 or 2 videos on black holes before. If you fell into a gravastar, you'd be extremely dead before you even hit the surface, ripped apart and ground down by the gravitational forces. And once your scattered remains touch the shell, the atoms you were once made of would probably break down and dissolve completely, only to be converted into the vacuum energy of the interior, making the gravastar an infinitesimal bit bigger and an infinitesimal bit more massive. Okay, this was fun and all, but what exactly is the point? Isn't this just another video of wild scientific speculation just for the sake of it? The point. Black holes were suggested more than a century ago as an abstract solution to equations of gravity. For more than 50 years, they were considered mathematically valid, but too absurd to be real. Few believed they actually existed. But scientists kept working on paper and looking at weird things, and then we saw stars being thrown around by invisible titans. We saw light stretching around invisible gaps in the sky, and as our technology and theories improved, we even sort of took a picture of them. We have evidence for them, and they fit our theories, and nowadays it's kind of common sense to accept them as real. Black holes are extremely elegant and fascinating, but they also created a lot of questions that have traumatized physicists for decades. Singularities literally break our best understanding of physics. They seem to delete information, which shouldn't be possible. Gravastars are a relatively new idea without any of those problems. They don't need singularities that break physics or delete information. They solve the puzzles of black holes, but they too create new problems, like weird exotic matter for their incredibly cold and tight shell, super dense nothing to make a supermassive empty core. But just like black holes, they do work on paper and fit what we see in the sky. So, are they real, and will we ever know? Actually, there is a way to find out. Black holes have an event horizon, while gravastars have a physical shell made of matter, which means that they behave very differently when they smash into each other. The collision of two objects as massive as they are creates huge amounts of gravitational waves, ripples in space-time that travel at the speed of light. You can think of them as the music of cosmic cataclysms. The collision of two black holes should sound like a bass drum, a deep thump that stops quickly. But two gravastars colliding should sound like a gong, leaving subtle echoes behind. Scientists are listening for these echoes in the music of the cosmos. Unfortunately, black holes and gravastars are surrounded by such strong gravity that it swamps most of the music. It's like trying to tell two instruments apart through a thick wall of concrete. You need very sharp technology for that. While we've made incredible progress in the last few years, we're not quite there yet. So this is where we'll end this story. Gravastars have the potential to answer some of the biggest problems in physics. Or they're just another idea for our discard pile. But this is why we do science. To learn that everything is different to the way we thought it is, until the day we truly understand the nature of reality. The universe today is happy and healthy, with exciting things going on. But at some point, the night will turn dark. Everything that once was will peacefully sleep forever. But what is the last thing that will ever happen, and when will it be? It turns out there is such a thing, and you probably haven't heard about it. Let's travel to the end of the universe and look at the last thing. After a messy birth, our universe was a sleepy baby, warm and dark, filled with swirling clouds of hot hydrogen and helium. The story of creation is a story of this gas and where it will end up. Shortly after, the universe got busy making the first generation of stars. They were massive and lived violent lives, forging new elements, only to release most of them when they blew up. Countless stars were born and refined the gas available in the universe, cycling matter around, each generation giving most of its gas and fresh elements to the next. But not all gas is returned. Every time a new generation of stars forms, they also make more and more red dwarfs that burn slowly and live for trillions of years. When they die, they don't give their gas back to the universe, but turn into white dwarfs. So red dwarfs lock up more gas forever. Some more gas is locked forever in other remains of dead stars, neutron stars and black holes, which is bad as it reduces the material available for new stars. Today, the universe is a great home for us and will remain so for billions of years. But most of the gas has been used up or trapped. Over 90% of the stars that will ever be born have been born already. To get to the last thing to ever happen, all other things need to happen first. The next few 100 billion years will be fun and a great time for galactic exploration. But step by step, large stars and stars like our Sun will die out. Eventually, almost all the stars will be red dwarfs slowly dying. The end of everything, but not quite. In a few trillion years, the cosmic gas will finally have run out. About 88% of the mass of every galaxy will be white dwarfs, 2% neutron stars and black holes, and about 10% gas giants and sad brown dwarf losers. White dwarfs are the corpses of old stars, not much bigger than Earth, but on average as massive as half our Sun, some even much more. This makes them the third densest objects in the universe, after neutron stars and black holes. About 1 million times denser than the Sun today. Since they used to be active stars, their surface can be as hot as 150,000 degrees. White dwarfs are dim, hot, dense spheres that don't do anything anymore. But eventually, even white dwarfs will die because they're slowly losing their heat. It takes at least 10 trillion years, more than 700 times longer than the current age of the universe. As they do their cooling down, the universe around them will irreversibly grow dark, as more and more white dwarfs burn out and turn into dead husks, black dwarfs. Spheres of death, as cold as space itself, invisible against the dark backdrop. Over trillions and trillions of years, every object in every galaxy is eventually either ejected into the void or its orbit decays and it will fall into the central black hole and be destroyed. In about a quintillion years, all galaxies have evaporated and every object is on its own, in the center of its own observable universe, emptiness as far as can be seen in any direction, traveling through black nothingness. Still, there are things that will happen. black holes are dying, slowly. They'll fizzle away by emitting Hawking radiation until they're so small that they die in a final flash of light. This will take about a googol years, 10 to the power of 100 years, until the last supermassive black hole dies. A number so absurd there's nothing to compare it to. Maybe some living beings could have survived around black holes, but even this science fiction option ends now. After this unsettling amount of time, we're not even close to the end. Now is the time of the black dwarfs. It turns out there's some weird physics going on inside the dead husk of stars. The weird physics of black dwarfs. A black dwarf is a sphere the size of Earth, as massive as a star, but almost as cold as absolute zero. Stars stay alive because of their intense heat in their cores, so why do black dwarfs not collapse into a black hole? What keeps them together? Deep inside a black dwarf, matter is squeezed to densities millions of times greater than anything we see on Earth. The pressure is so great that electrons can't combine with the nuclei to form atoms. Instead, matter is weird, degenerate. The nuclei are compressed by the weight of the star, locked into a rigid lattice, while the electrons form a plasma between them. And these electrons hold the star together. We're simplifying, but imagine matter as a subway train and electrons as passengers. If there are empty seats, passengers spread out because they care a lot about their personal space. But as a black dwarf is so incredibly dense, this is like squishing more and more passengers into our train. Gravity is pushing in, trying to collapse it. The passengers are forced to sit and stand close together, which they hate. And so the passengers, our electrons, try to push out against gravity as hard as they can. This way, the electrons that are having a horrible time in the crowded train that's the black dwarf hold up the star. Everything else in the universe may have crumbled already, but these tiny particles push against each other until the end of time. Or they would, if quantum mechanics didn't ruin everything. Simplifying a lot, when particles get close enough, sometimes they can jump at each other and fuse together, a process called quantum tunneling. This happens constantly in stars because of their intense heat. It's one of the key reasons stars can fuse elements into new ones. But it also happens at a temperature near absolute zero, just, well, mind-numbingly slowly. This is the final step to creating the last interesting thing to ever happen in our universe. Here, in this lone black dwarf, something fantastic occurs. Nothing happens for 1 trillion years. Nothing at all. Can you imagine that? But then, a single fusion reaction. 2 carbon nuclei combined by quantum tunneling to become magnesium. Another 100 trillion years pass. It happens again. Then nothing for another bazillion years. Oh, 2 oxygen nuclei combine into silicon. As eons pass, the nuclei in the frozen black dwarf slowly combine, making new heavier nuclei. And these take even longer to fuse, but given enough time, they eventually will. Remember the breathtaking amount of time it took for a supermassive black hole to evaporate? That's a brief moment in comparison to what's going on here. The difference between a second and trillions of years has lost all meaning. Over a time so absurd that it has no name, nuclei keep fusing into heavier elements. Until, when silicon nuclei fuse, they form nickel-56. Nickel-56 is radioactive, which means it's unstable. And when it eventually decays and turns into iron, it emits 2 positrons, antimatter electrons. And these 2 positrons find 2 electrons and annihilate them and themselves. Which is a problem. Remember how the uncomfortable electrons produce the pressure to hold the star together. Destroying the electron means fewer friends to help them hold up the star. Losing an electron does not give them more space to scratch their butts, it just makes gravity squeeze harder, the walls closing in on those that remain. In the case of the most massive black dwarfs, this is catastrophic. Bit by bit, the black dwarf turns into a sphere of iron and more electrons are annihilated. For at least 10 to the power of 1,000 years, almost but not quite forever, there's no visible change in the entire universe. And then, finally, the last thing to ever happen happens. The black dwarf has lost one too many electrons. It can no longer support its immense mass and goes into an uncontrolled collapse, a supernova. It first implodes and then explodes as bright as a galaxy and fills the empty universe with light again. A beautiful moment nobody will get to enjoy. And then, as quickly as it began, it's all over. Darkness again. Emptiness. Space travel is the most exciting and challenging adventure humanity has ever undertaken. But in an irony of history, we may stop ourselves from going into space the more we do it. With every rocket launched and with every satellite deployed, we're creating a trap for ourselves that gets deadlier and more dangerous every year. If it's ever activated, it could end the space age and trap us on our planet for decades or even centuries. Getting something into space is incredibly hard. To do so, you need to move very, very fast, at first straight up to leave the atmosphere, then sideways to begin a sort of circling around the Earth, still very, very fast. If you do that successfully, you can enter a low Earth orbit. And once in orbit, it's very hard to get out of orbit. Unless you have energy to spare, you're sort of locked in here, falling around the Earth forever. That's great for things we want to stay up, like space stations and satellites. And so we moved the majority of humanity's space infrastructure to this place, just a few hundred kilometers above the surface. Just high enough so that the atmosphere is so thin that orbiting things can stay up for centuries before air resistance can slow them enough to bring them back to Earth. But this is also the source of our deadly trap. Rockets are really metal cylinders that keep big piles of fuel in place. Whenever a portion of the fuel has been spent, the empty tanks are dropped to make the rocket lighter. Some parts crash down to Earth or burn up in the atmosphere. But most of the useless rocket parts stay up and begin to orbit the planet. After decades of space travel, low Earth orbit is a junkyard of spent boosters, broken satellites and millions of pieces of shrapnel from missile tests and explosions. Right now, we know of around 2,600 defunct satellites, 10,000 objects bigger than a monitor, 20,000 as large as an apple, 500,000 pieces the size of a marble, and at least 100 million parts so small they can't be tracked. This debris is moving at speeds of up to 30,000 kilometers per hour, circling Earth on crisscrossing orbits multiple times a day. Orbital speeds are so fast that being hit by debris the size of a pea is like being shot by a plasma gun. On impact, the debris vaporizes, releasing enough energy to punch holes straight through solid metal. So, we've covered the space around our planet with millions of deadly pieces of destruction. And we also put a $1 trillion global infrastructure network right in the danger zone. It performs critical duties essential to the modern world: global communication, GPS and navigation, collecting weather data, looking out for asteroids, and all manner of scientific discoveries. Things we would miss very much if they suddenly went away. If just one pea-sized bullet hits one of our 1,100 working satellites, it will be destroyed instantly. 3 or 4 satellites are already being destroyed this way every year. As the number of satellites and the amount of junk in orbit is expected to grow tenfold in the next decade, we're approaching a tipping point. But the worst thing in space is not tiny pieces of junk. The worst thing would be an unstoppable chain reaction that turns a lot of non-junk things into junk. For example, if 2 satellites hit each other in just the right way. If satellites collide, they don't stop and fall out of the sky. It's more of a splash than a crash. Orbital speeds are so fast, solid pieces spray right through each other, transforming the 2 satellites into clouds of thousands of little things still fast enough to destroy more satellites. This could trigger the slowest and most destructive sort of domino effect, a collision cascade. Like a shotgun spray, each collision creates more bullets. What was once a single tiny target, very unlikely to hit anything, becomes a wall of destruction, hungry to make more. As more and more satellites are destroyed, the destruction accelerates exponentially, eventually destroying everything parked in orbit. But space is very empty, so the first few collisions may take a long time. By the time we realize what's happening, it's too late. 1 year, 1 satellite is destroyed, and that's no big deal. The next year, 5. The year after, 50, until there's nothing left. The situation in orbit is rapidly worsening, and we may already be past the point of no return. Within 10 years, space around Earth may no longer be viable for long-term satellites or rockets. The worst-case scenario is horrifying. A debris field made of hundreds of millions of pieces, many too small to track, moving at 30,000 kilometers per hour. It would effectively create a deadly barrier around Earth, possibly too dangerous to cross. Dreams of moon bases, Mars colonies, or space travel at all may be set back centuries. And the loss of our space infrastructure would send some of the technology we rely on daily back to the 1970s. But it might not be too late to clean up our mess. While the space industry has become better at avoiding space junk, it's still growing fast and occasional weapon tests don't help. So there have been a couple of wild but also serious suggestions about how to quickly remove as much deadly space junk as possible without creating more in the process. Lots of ideas are being thrown around, and some of the most seriously considered involve capture and return missions, which are being tested now. One method involves meeting a piece of junk in orbit with a small satellite loaded with a net. Once caught, a small rocket could be used to bring it down towards Earth. Targets too large for a net might be instead caught with a harpoon on a tether. Instead of firing a rocket, the cleaner would deploy a large sail to produce atmospheric drag and accelerate orbital decay. And there are lots of other wild sci-fi sounding proposals too. Some might use giant electromagnets. These magnetic tugs work by pushing on the magnetic components inside satellites that they use to stabilize and orientate themselves in Earth's magnetic field. These may be safer and more reliable than nets and harpoons because they never have to make contact with the junk they're handling, so there's no risk of accidentally breaking up their target into more junk. As for the tiniest bits of junk, lasers might be the key to vaporizing them entirely. Satellites with lasers wouldn't need to visit their targets, they can shoot them from far away. Large objects can't exactly be shot down, but lasers can be used to ablate them or burn tiny amounts of material off the side to push the junk to a safer orbit. Whatever technology we use in the end, we better start doing something soon, before 100 million bullets become a trillion and the trap is set. If we don't act, our adventure in space might end before it's even begun.